All right, only 45 minutes to go, folks. We'll see you all shortly. It's Peter Hanson's here from the Data Range Bytes team. See you in 45 minutes. Hello, everyone. Welcome to DataEng Bytes, a community-built conference that showcases the best of data engineering right here in Australia and around the world. My name is Peter Hansens, and I am the founder of Cloud Shuttle, a community-focused cloud consultancy, as well as the organizer of the Data Engineering Meetup here in Sydney. My co-host is Simon Aubrey. Please introduce yourself.
Oh, thanks, Peter. Hi, my name's Simon Aubrey. I'm a principal data engineer at ThoughtWorks in Sydney, Australia. I'm also the co-organizer for the Sydney Data Engineering Meetup. Now, I've got a passion for all things data, but especially streaming systems. However, before we commence today, let's take a moment to recognize the lands upon which we meet. I acknowledge the traditional custodians of the various lands on which we meet today, and the Aboriginal and Torres Strait Islander people participating in this online conference. I pay my respects to elders past, present, and emerging, and recognise and celebrate the diversity of Aboriginal peoples, their ongoing cultures, and their connections to the lands and waters of Australia.
Today we have a packed schedule full of incredible talks. Zhamak Dehghani taking us through an introduction to data mesh. Charles Feddersen will be talking to us about developing end-to-end analytics solutions with the latest Azure Synapse features. Dom Collier will be building a code-generated data platform. Vidya Venugopal will take us through ever-changing data models, schema management for the future. And then Lewis Lee will talk to us about Snowflake Cloud Data Platform.
Thanks, Peter. But that's not all. Closing out day one, we also have speakers, Mike Gulian, who's going to be sharing data team as an optimization problem. Jana Segal will be talking about automating machine learning pipelines with Kubernetes and Airflow. Marta Miura will be sharing change data capture with Flink, SQL, and Debezium. And closing out today, Robin Moffat will be sharing how to build a Telegram bot with Apache Kafka and KSQL DB. Now, all the talks today are pre-recorded, and most of our speakers will be joining live right after their talks. Our speakers will be able to answer questions via Slack and also live once they join us. Now, today is not just Peter and I talking. We're going to have a number of guest hosts who are also our co-organizers, and they're going to join us at different times and conduct the Q&A sessions with our guests. So it's going to be fun, and I'm sure we're going to be both entertained and learn a great lot. Now, an event like this is only possible with the support of our wonderful sponsors. So I wanted to take a short moment to acknowledge and thank the sponsors of Data Engineering Bytes. We've got Snowflake, MongoDB, Databricks, Amazon Web Services, Fivetran, Confluent, Microsoft, ThoughtWorks, Instacluster, Canva, Yao, and Cloud Shuttle.
We will also make all talks public after today. So if we have any technical issues or if we miss a talk, you'll be able to watch them later too. It's important to remind everyone that we have a code of conduct. Please be thoughtful and kind to one another. Please act with respect and behave. We will have moderators on YouTube and make sure that everyone adheres to our code of conduct. Finally, we are going to distribute a survey, so please fill them out. It will help us figure out how to make the event even better next year. And a quick plug, please follow myself on Twitter at Pete Hansens and Simon Aubrey at Simon Aubrey. We always love to hear from data engineers and those wanting to get involved in the local community.
Thanks, Peter. Well, let's not waste any more time. It's time to welcome our first speaker, Zhamak Dehghani, who's going to be delivering our keynote today, Data Mesh, the next generation of analytical data platforms that shifts to a paradigm drawing from modern distributed architecture, considering domains as a first-class concern, and applying platform thinking to create self-serve data infrastructure, where ultimately you're treating data as a product. Now, I'd like to take an additional moment to tell you about our keynote speaker today, Zhamak. Zhamak Dehghani works within ThoughtWorks as a technical director of emerging technologies in North America. She's a member of the ThoughtWorks Advisory Board and contributes to the creation of the ThoughtWorks Technical Radar. Zhamak has worked with software engineering and as an architect for over 20 years in the areas of distributed computing communications, as well as embedded device technology, and she's contributed to multiple patents. Now, one of Zermac's favorite activities is running the trails. And after many years of exploring the beautiful trails here in Sydney, these days she runs the trails of the San Francisco Bay Area. So let's get Data Engineering Bites underway, and over to you, Zermac.
Hi everyone, I'm Zermac. It's wonderful to connect with you across the Pacific, as you can see in my virtual background, and talk about data mesh. So for today's session, I have two goals. My first goal is to get you to stay with me for the next 30 minutes and not swap windows or walk out of the room. And my second goal is to introduce the concept of data mesh, introduce the rationale behind it, what got me so frustrated to start writing about it and talking about it, and also share with you a little bit of how to. So it's been about 2 years since this hypothesis, I guess, came out, and we have started implementing it with our clients at ThoughtWorks. So I can share some of the learnings and some of the how-tos, I guess, with you as well. And when we connect live, hopefully I get to answer anything I didn't address today, and I can answer that in person. All right, let's get started. Hopefully you can see my screen now. Introducing data mesh, a paradigm shift in analytical data management architecture. But before we start talking about data mesh and data architecture, what do we really mean by data? I think there are two camps and two categories of data when we talk about data. Operational data, which actually sits underneath the business APIs and applications that serve the business, run the business, satisfy the customer needs. And these databases often keep the current state, right? And we run CRUD operations on them. We update the current state. And we say this is the data on the inside, and we put APIs and applications on top, and God forbid, if ever somebody else would go through these databases and get this data out, right? And I think over the last few decades, we have mastered the technology around it, the best practices around kind of operational data. We have polyglot modes of, I guess, sharing and storing and getting access to the data, depending on the need of the application. Next to that, or maybe actually far, far from that, sits the analytical data, right? Often what we call big data, because analytical data is there to really show a historical snapshot, a longitudinal view of the business as it has happened, with the purpose of optimizing the business, right? Be able to run reports so we see how how the customers are behaving, how the market is behaving, how our application is being received, or be able to train our machine learning algorithms so that we can optimize the performance or the experience of the user. We can optimize the pricing. So there's a lot of optimization problem space being answered by the analytical data. And traditionally, we've had these either ETL jobs to get data from this operational world to analytical world, two separate worlds, a fragile approach to kind of sync these two worlds together, or sync at least one with the other, or in the more modern world that we're very proud of, through events and event streams, get data from one place to another. So for the next few minutes, I want to talk about these kind of architectural patterns that we have seen in the analytical big data world, how have we been managing this world. We started with data warehousing. The concept behind data warehouse was that, okay, those the wheels at the top are their operational systems that are running, and they have some databases. We will run these scripts and processes, or through drag and drops or writing code, to extract data out of these operational databases, then transform that data to some other forms. Often the language gets lost in that transformation, but to some other forms that often is representative of some sort of a multidimensional schema that we will store. We will load into the data warehouse, ETL, and allow downstream people come and run SQL queries on it so that they can run reports and analytics on top. That was okay maybe for a while, and this is the kind of the technology landscape that exists to support that paradigm. You know, you will see things like Google BigQuery or Microsoft Power BI or kind of Snowflake that really tries to put data in a modeled form in one place. And I know some of these technologies, in fact, like Snowflake, they actually do support semi-structured or unstructured data, so they can be used at data warehouse or other forms of data storage. And then on top of these kind of tooling and the storage and modeling, you have your lookers and tableaus that allow you to do reporting and visualization and querying on top. Around 2010, we decided that, well, you know, the data warehousing is great, but it's not really working for the modern world, where we want to get access not only to this perfectly modeled data, or as James Dixon put it, perfectly bottled water, but we want to get access to that noisy, unstructured, raw data, because that's where the insights sit. Like, we want to see data as it happens in the business so that we can use it for data science purposes. So we call this model data lake. So it's more or less the same paradigm, as in we're still extracting data from those operational systems, but instead of transforming them first, we load them first into this now not bottled data lake in its raw format, with the hope that we can unleash the data scientists to get insights out of it. And then once we figure out what parts of this data could be helpful for different business domains, for those domains we come and model the data, we call them data marts, and give them through APIs or SQL databases or whatever format that they need, and is fit for purpose for them, and we create these Lakeshore marts. And the technology that supported that paradigm, or that architectural paradigm, where, you know, a series of kind of semi-structured big data storage, like the, you know, the blob storage, different kinds of blob storage. We needed, you know, tooling to be able to orchestrate these workflows that are still extracting, and pipelines, the data pipelines, I guess is the word or phrase we use, to be able to run these jobs and orchestrate them, to move data from one end of the organization to another end of the organization, and one end of the architecture to the analytical architecture. And then language that allows you to run these, I guess, queries and modeling over the large amount of data across this semi-structured storage. The modern version of that is do the same, have the same paradigm, but do that on the cloud. So this is this example or solution architecture from GCP, cloud architecture, data lake on cloud architecture, Amazon, Azure, pick your, you know, favorite provider. More or less they look the same, it's just different probably icons and names of products. But if you look at this diagram on the left hand side, the yellow part is still the source systems, operational systems, somehow through batch or streaming get the data into the lake, the purple box, and then downstream you feed it into a little bit more fit for purpose ways of accessing it. So if we zoom out, regardless of lake or warehouse or lake on the cloud, there are certain characteristics that are shared between these approaches. The first characteristic is that all of these assume a centralized monolithic architecture where ubiquitous data across operational domains needs to come in, and it needs to serve the, you know, the multiple use cases, numerous use cases, and as you can imagine, the result of this characteristic is that you will have a bottleneck here, right? Often these monolithic architectures, monolithic team and operational model leads to unsatisfied people on the right, that they're always ahead of what the platform can offer them. Probably frustrated folks in the middle because they don't really understand what the data is about and have to make meaning of it, and a bunch of probably oblivious people on the left-hand side because they have no understanding or no interest or no incentive to care about what happens to the data when it goes to that centralized platform. And often those people in the middle that are under sheer pressure to satisfy the needs of, you know, people on the right, without really talking and knowing about people on the left who are producing the data, or a group of hyper-specialized, you know, pick your title, data ML engineers. And they are there because they know the tooling of that world. They know how to use that tech stack, but they're really far, far, far away from you know, the domains, and they're far away from the actually understanding of the data itself. And there's always this gap there's always hard to find these data engineers, these specialists, and they don't really have a great life. They're under a lot of pressure without really understanding this data that they need to turn into assets. What does it mean? Where it comes from? Where it goes? Who's going to use it? So it's a bit disconnected. You see the walls, and I didn't draw the unhappy faces on other presentation. I usually put some unhappy faces on the face of these ML engineers or data engineers. And often what happens, I saw with a lot of kind of the clients that I work with, this monolithic architecture doesn't work. The job of architects often is, how can I pull things apart so that I can operationally scale, and then how can I integrate them back together? For some reason, we've been fascinated by this concept of pipelines in this world of analytical data. The concept of getting data into various stages, the ingestion stage of getting data from many different sources, and use all sort of trickery so we can make that really efficient, I suppose. And then, the stages of transformation, the stages of serving and building APIs. The challenge with this model of architectural decomposition is that any data-driven change or feature, imagine you want to, unlock a data asset from a new domain, you want to create a new data assets around a new entity in your business, and that requires change across all of these stages. So this architectural decomposition doesn't lend itself to an efficient operational model, and this operational model is still full of friction. And in terms of execution, as you can imagine, use cases on the right-hand side are disconnected from the left-hand side where the data comes from, and the platform is disconnected. Often the execution is, let's build the platform first, and then use cases come, or let's build some point solutions and then we unlock the data. It's a very difficult thing to bootstrap, and then that's how we've been, building for the last 40 years. That hexagon that, the hexagon that I showed at the beginning, which was, analytical data architecture. That's how we built it. Centralized architecture, hyper-specialized silo of people, and through disconnected execution. And the failure symptoms that over and over, at least I've seen, are really around scale. It's perfectly fine to have a centralized team, to have a couple of data engineers in the corner of organization, try to figure out, how to create some sort of an analytical view of your business for a couple of domains. It's a very different story when your number of domains grows and you have a rich business and you have a mission to become data-driven, right? So the failure modes I want to emphasize are around scale. If your business growing above a certain scale in terms of number of domains, and if it's really becoming data-driven, so data really becomes an integral part of running your business, these models have the failure modes and the points of friction that I mentioned. And that's what we've been doing, right? We've been kind of changing from having some sort of an evolutionary change through warehouse lake to the cloud, but fundamentally the failure modes remain. Where do we go from here? So I want to introduce to you the thinking or the underpinning pillars of data mesh that contrast the model that you saw, independent of the technical implementation. I think the first thing that underpins data mesh is that if you decompose your architecture around your big data, storage and access, consumption and storage and access, is around the axis of domains. So, domains could be aligned with where the data is actually being produced, or the points of origin for your data. So imagine in a health insurance, if you're in a health insurance or any other sorts of insurance, there is probably a member management, member admission domain, and it has its own applications and services, or maybe microservices. So the big data for that domain should be oriented and should be next to those services and applications and owned by the people that are running the member admission. If you have a domain around claim processing and there have a bunch of applications that real time is processing claims and responding to the claims, then the data, big data, that analytical view of the claims over the infinite log that demonstrative of what claims has been lodged or rejected or approved, that domain and those teams will also become responsible now for sharing that big data. So if you bring that domain thinking, we end up with a bunch of domains that are oriented around the source, a bunch of domains that are newly generated and never existed. There's no system around them because they're representative of the aggregate from multiple domains, and there will be domains, big data domains that are oriented around the point of consumption and become more and more fit for purpose. So really decomposition, not decomposition of architecture and storage and access, but most importantly, decomposition of ownership is around domains. The second pillar or principle behind this is that, well, we say data is asset. Let's get real. What does it mean, data to be an asset? So the second pillar is the people that are responsible. And I know that this is a very highly, deeply technical subject, but I keep bringing your focus to the people because it requires a shift of behavior and a shift of incentive. So I want to start the conversation with people and changes and then go to technical details of this. So in this model, the people that are now owning the data, that the centralized ownership that we talk about, are responsible to serving that data as a product, are responsible for happiness and satisfaction of those data users, the data scientists and the data analysts. They've got to remove all of that waste time from their workflows, which is around where is the data, where can I get it, how do I make sense of it, how does it actually link and relate to that real operational domain that we talked about, and can I trust it? So all of those points of friction in the life and workflow of a data user needs to be removed through treating data as a product. And that means data should be discoverable, should be, the truthfulness of it should be measurable, should have some SLOs, it has to have documentation, has to be trustworthy. The security needs to be applied at the granularity level of this data product. So the data product owner needs to keep KPIs around the net promoter score and the satisfaction of the user. It should should be measured maybe by the growth of the users of that data. So that's a very inverted model to how much data can we keep in one place, but not how many consumers can we empower. The third pillar of this is that, okay, if you're talking about a distributed model, a decentralized ownership, how do we actually make it real? How can we remove, again, the double work that each of these domains need to do? It's not easy to provision data pipelines. It's not easy to provision policy management around them. It's not easy to provision large data storage consistently. So the job of this layer that we call kind of self-serve infrastructure layer or data platform layer is really the job of a group of people whose job is really remove friction and create higher level of abstractions for those data domain people to be able to product data products. And I know in a lot of your organizations already you have these data infrastructure folks, and what they do is they provision Kafka for you, they provision a namespace on Databricks, they provision, some sort of a big blob storage, but the job of these folks go beyond and above that, and I will go through the details in a minute, to really abstract away those complexities and change the language. The language that those data product developers need to talk about is, I want to provision a data product that gets data from this place and it does this sort of transformation and serves in these modes of access, and that's it. The rest should be abstracted away, and that's the only way we can kind of get to this level of autonomy, I suppose, by those teams, and convince them to not only run their business on APIs, but also now own their big data as well. So the final pillar is really around the governance model, because how do we create interoperability? If I use the analogy of APIs and kind of microservices world, because in microservices world, we also went to a distributed, decentralized model, but what we take for granted is the existence of standardization around the interconnection of the services, right? We take for granted we had HTTP, we had REST, we agreed on some fundamental, ways of communicating between each other, and that unfortunately doesn't really exist. There are some standards out there, like, how you define your schema or your reports, unstructured files, but really we are missing those fundamental interoperability mechanisms for these systems to data sets to talk to each other, to speak a similar language, and so on. So there is a federated, really, governance model that needs to be created, and then that governance needs to be codified in that platform, right? So if we say this is how we're going to demonstrate timestamp or the access of time for our data products, data platform should be codifying that and really giving you SDKs or other ways of being able to encode data according to the standard of how you demonstrate access of time, as an example. So in summary, really, you want to also build this whole ecosystem around this concept of connected intelligence. Think about your services that are those points of actions on the top and interactions with your customers, generating data as part of their domains. And as you go through, multiple maybe, ML-based or data-driven use cases or business cases in your organization, bring this platform to life. You start thinking about, as you go through execution of say, 1 or 2 or 3 data-driven use cases, whether you're using ML or whether you're just using reports and you want to bring those reports to life. Think about, okay, what domains do I need to bring on as, activate as my data products, and then what data infrastructure do I need to put in place to support those domains and really run these iterations many times until you get to that level of maturity that's really needed to create those autonomous teams. So underpinning pillars of data mesh, domain-oriented decentralization, and most importantly, domain-oriented ownership aligned with your existing operational domains. Data as a product to remove friction for data users. Self-serve data platform to create those autonomous data product developer teams. And finally, a model of governance that is oriented around interoperability between those data products, oriented around creating an, well-playing ecosystem, right? And that's a different value system that we currently have around data governance. Data governance is very much around centralized modeling of the world, so that model is universally true and would never change. And that's a fallacy because the real world doesn't work that way. Things change. So this is the part that I want to go a little bit deeper. Let me check. We have only 8 minutes, so we'll see how it goes. All right, so I talked about these hexagons with lines in them, and I call them data product. What do they look like? It's great that for any concept that gets introduced, we create a domain language, right? So for this concept of a data product or a node on the mesh, we created this model. And this model might change over time, but this is the model we have today, which is around every one of these nodes, every one of these data products is receiving data from somewhere else, right? That somewhere else might be actually the microservice that the same team is developing, or it could be an upstream data product. So we have this concept of polyglot input data ports that receive data from upstream, either data products or the application that's sitting side by side, as in logically sitting side by side to it. It has a set of polyglot output ports that allows big data access to the user. So it can be through streams, or it can be through unstructured Parquet files on some sort of blob storage, or it can be SQL queries, whether you're using a SQL engine on top of your blob storage like Dremio, or using, a big table or something like that. And for this data product to be able to get configured, you need to have a set of APIs around and be discovered, a set of APIs that let this data product to be discovered, right? Introduce yourself, data product, like what is your name, the ports that you're providing, the address of the ports, the schema for those ports, the metadata, and the SLOs that you're supporting. There's a whole lot of, management that we call these control ports that are served through APIs. And as you can see, I don't really talk about pipelines because I don't think they matter, to be honest, so much. Pipelines that are around ingestion from those input ports and processing of the data and serving through those output ports are truly second-class concepts. They are hidden. There's some implementation details. If you want to use Databricks and Spark, then that's awesome. If you want to just use a bunch of services functions, that's great. That's an implementation details. We can talk about those in another session, but I want to just say that shouldn't be the main concern. The main concern should be, what is the blueprint? What are the interfaces to this data product? What are these ports? And let's standardize those. Let's consider this the quantum of your architecture that can be independently deployed, and then we can talk about the implementation of the data pipelines underneath it. These data products providing read-only data. We're not updating data through these ports. We're adding and appending data. And that's truly important because, and I really hope that we come up with a good standard, and would be my focus for the next few months, to come up and publish those standards, that we respect time as an ever-present access of this data, as in you would always query, tell me the information about this member for this point in time, or for these 2 points in time. And that's really important for analytics purposes. If you want to know that current address of a particular member, wonderful. Just go to the microservice or the APIs that manages the members. It's really a different problem than the analytical queries that you make or APIs that you make on top of this data. What does the mesh itself look like? So the mesh is really the connection of these data products, and I have to admit that I didn't put the actual applications that feeding data into the mesh. They're there. They're the plane underneath it. I didn't draw them, but they're there. That online claims here is getting data from probably some stream from an online claim processing system, or the call center claims is getting claims from a change data capture out of a legacy database that nobody knows how that application works. Because it's just so old. And the claims as an aggregate is a data product that is consuming from those 2 upstreams and creates an aggregate view of all the claims. And down there, claims trends is probably a machine learning data product that is showing different cohorts around the domain. I have to say, I'm not super happy about the control plane naming. This is a very common networking paradigm. Service mesh uses the same language. I'm not being very innovative here in my naming, I have to admit. But data mesh, any mesh architecture or networking architecture has this control plane idea and a data plane idea. And control plane job is really control and administering and configuring and controlling. It's basically centralized pieces of this mesh. I will change this name. I just don't have a good enough name. And the reason for that is that I don't want to give this perception that there's these centralized pieces that without them, this mesh will not exist. In fact, I want all of these data products to be completely independently, sustainable and have all the features that they need. And this plane is really, control plane for is convenience. So be able to discover and explore this mesh, be able to see the lineage of all the data that is flowing through this mesh. It's wonderful to have a centralized tool, but that centralized tool hopefully relies on individual nodes on the mesh. Governance, policy management, who can access what, be able to debug this mesh and observability and apply guardrails so people don't do crazy stuff. You will actually see that people will do crazy stuff, try to map their data warehouse to a mesh. We shall not do that, but some people will try to do that. So you have some health checks and observability, probably graph traversing algorithms to just make sure that this mesh is somewhat healthy. And that really fits in that centralized pieces of the architecture. And the data infrastructure that we talked about, right, that really allows that self-serve functionality. You will have a basic delivery infrastructure, like, give me a storage, give me a computer cluster, and so on. But on top of it, you will have, discoverability tools, policy management tools, probably, hopefully, some sort of a blueprint, some sort of a SDK that allows data product developers really easily declare their data product, and they really focus on their transformation code and don't focus too much around how this transformation gets provisioned and gets run and what's the runtime environment. And that's through some sort of a SDK, and really focus as the platform layer or infrastructure layer on that data developer experience. Often the personas that we think about once where we develop this layer is the data developers, data product developers, data users, data scientists, data analysts, and sometimes even application developers that want to use analytical data, feed it into their databases. I want to talk about a little bit about team structure. This is actually from a real project that we're running. So some of the boxes may not perfectly match what I just described because I copied and pasted from a project I'm running. But if you think about the team topologies, is a great book, and I've put a link here on the slides. If you think about the team topologies, when you're running a mesh, you really have the platform team that in itself has a bunch of streams. Maybe you have the platform discovery stream, the platform blueprint team, or policy management, and so on, which is the red box. And on top of it, you have these data stream teams, which are essentially your operational team, plus their data developer brothers and sisters in the same team that are running the data products as an end-to-end feature or as an end-to-end, business-facing concept, because data is a product for the business, on top of the platform. And then you might have, your solutioning or enable team that are cross-functional and going across. You may choose to separate between your pure infrastructure to your core, which are like the high-level abstractions, or in our case, we have a bunch of accelerators that we focus on for the developer experience. We constantly think about how can we reduce the time of a data product to be activated on the mesh and really come to exist. So continuously evolving those accelerators that are consuming the core capabilities and infrastructure capabilities. And last, I want to talk about governance a little bit, because governance really in this model changes. Governance today is all about, as I said, one beautiful model, universal model, and let's define that model and let's hard code that model into some sort of a, warehouse or some other application. And governance here is different. Governance is about ecosystem thinking. It's about enabling interoperability. So what you find is creating this nexus and groups of, domain data product owners that come together and really define their domains, and any seams, any concept that goes across domains, and usually those exist like customer and so on, to come to agreement as how we should be representing this. You will find yourself running these continuous efforts around finding the data products and their boundaries and who should own them. And sometimes it's easy because they're associated with the source system, and sometimes they're easy because they're associated to consumer systems. But a lot of the times that you find things like, fraud detections or fraud data and things that are cross-functional, or marketing is the best owner for it, but marketing often doesn't have the engineering capabilities. And that's really the leap that needs to happen. If you want to be data driven, it has to be an integral capability of all functions of the business, right? So you find yourself running these sessions, continuously thinking about this data products and boundaries. Again, you want to push the definition and modeling of the data as close as possible to the actual owners, right, in the domains. However, there's always things that you want to standardize, and you want to globalize, optimize globally, right? And those things are how we represent time, how we represent customer, how we represent IDs that can be URNs that refer to upstream data products, so we can follow lineage. So those things you end up in a centralized way defined through that federated group of data owners. And as much as possible, in the last point, encode all of that into your platform and automate governance, either through upstream, like as a CI/CD pipeline of that data product, through checks and balances that you put there, or as part of observability and health checks that you continuously will run on your mesh. So what's next? As Alan Kay said, the best way to predict the future is to create it. And we are creating the future here. A future that doesn't quite exist. The paradigm maybe exists. The notion has been developed and is being fleshed out. The principles, I think they're there and perhaps non-negotiable. But what doesn't exist is technology that really enables this. I have to say, the actual technical implementation under all these wonderful things that I talked about, to me they're wonderful at least, is a little bit awkward. So you have to stitch together a lot of different technologies to kind of create that autonomous unit of a data product. With a lot of cloud providers, you find yourself that the notion of independent unit for these, it doesn't exist. You run out of storage accounts. It's a real problem as soon as you grow this number of data products. So the technology needs to catch up. But I'm really hopeful. I'm at the epicenter of this change, and I'm seeing a lot of great work is coming from big and small startups and large scale, I guess, tool makers. But for this paradigm shift to happen, I think we need to really change our view and how we look at this world, right? We want to move from this centralized ownership to decentralized, from monolithic to distributed. Hopefully, I can remove the word of pipeline from a language. Pipelines exist, but they're not the most important thing. Domains as products are the most important thing, or the data for around domains as products are the most important thing. Instead of really thinking, operational teams thinking about data as a waste or as a byproduct of what they do, they look at it as a product and they're incentivized around to do that. And we need a different language for this new vision of data analytics architecture. And the language on the left is the language I want to see less of, and the language on the right is the language that I want to see more of. Really focusing on serving the downstream people rather than downstream people try to ingest and consume whatever is thrown at them, right? Really think about the consumers as the main audience. Think about the interoperable ecosystems. So this year, InfoQ recognized data mesh as the innovators, one of the innovators, I guess, architectural trends. And I think last year and this year has been more about what is data mesh, and it's going to be, we're going to go into more how to do data mesh, and for the years to come, it's going to be how to do data mesh right, because we're going to get it wrong and we're going to iterate over it. And hopefully we will see this convergence of operational world and analytical world, as the operational services and analytical services are just two planes of the same domain sitting on top of each other, rather than being two separate entities across the organization. And the journey of 1,000 miles begin with the first step. And you have taken the first step. You've been curious enough to come and sit and listen to me about this. And hopefully I kept you in this window and you didn't run away halfway through. And thank you for that. And thank you for your attention. And I'm looking forward to our Q&A together.
Oh, thank you. Thank you very much for that presentation, Zhamak. Now, you challenged us to hang around. And absolutely, we sure did hang around. That was a fantastic presentation. Absolutely brilliant. One might say a perfectly bottled overview of data mesh. Now, if you've got any questions for Zhamak, please remember that we've got dedicated Slack channels for each of our speakers today. And very shortly, we'll be sharing a QR code so we can get your valuable feedback. Now, I wanted to welcome Zhamak. Hi, Zhamak. How are you?
I'm good. How's everyone?
It's really great to have you join us live today. Thank you very much. That was an excellent presentation. Now, if you don't mind, if you've got a few minutes spare, I'd like to ask you some questions that we've captured from some of our audience today on Slack. Do you have a few minutes to answer those?
Of course, more than happy to. It's about 9:42 p.m. I'm sure I can hang around for another 15 minutes.
Fantastic. No, we really appreciate you joining us. So I've got a question from Senthil Kumar. He asks, Zhamak, that's a great talk. So his question is, does data mesh serve the data warehouse? And if so, how different is it from master data management for reference data entities?
That's a great question. I think the data mesh addresses the concern around sharing core data entities or core domain, I guess, data sets in a way that, the more usability or reusability or sharing use cases that you have, the more that data sets lend itself to be on the mesh rather than off the mesh. However, data warehouses still has a place. Like the areas where we have implemented the data mesh, data warehouse often finds itself in two places. One is data warehouse is still a fairly, or data warehouse / BI tooling is still a fairly good solution as an edge node, where you have modeled the data and you do want to run queries on that perfectly modeled data as an edge solution, not as a solution that necessarily, would feed a lot of different composition and a lot of different use cases. That's one place that data mesh can serve data warehouse as a source, and I guess data warehouse being an edge consumer that is serving, instead of sharing a lot of data, maybe serving more fit for purpose use cases. The other place that data warehouse finds itself is when you implement this brownfield, which is majority of cases, you have a few enterprise data warehouses lying around, and they have had their own proprietary pipelines and so on. And then data warehouses start, the plan usually for those data warehouses is retire, and over time, get the node on the mesh directly under the supervision and control of the people who build the source systems, and get those data nodes closer. But as an interim solution, often you may end up with a case where data warehouse still feeds the mesh, and then over time you get that ownership back to the source domains and retire the warehouse. That's another model that we've seen as that just allows you to bootstrap your platform.
Awesome. So I've got another question from Slack from Kay. What are the challenges, Zhamak, for organizations trying to transition to a data mesh architecture other than a mental shift? And for new organizations excited to try out data mesh, how could we tell when the organization is ready for one?
All right, how much time do we have for this question? Don't let me get started. So on the organizations that has had a strong, data culture in terms of data warehousing, I would say, and a strong maybe analytical culture, there is a continuous education and evangelism that need to happen. Just as simple, and a lot of it is around mind shift, but just a simple change of perception and understanding that data is not static. When we talk about data product, we're not just talking about data. Data cannot exist in isolation. So what we are doing with data mesh, we're combining code that transforms, serves, and stores the data, as well as the data itself, as well as the underlying technology that can serve that code and data as a quantum of architecture in a way. Bring that together and wrap it around and say this is one unit of your architecture plus infrastructure, and we call it a node on the mesh. Just to get people get their head around. Data is not just a table or a file, it's the code, it's CI/CD pipeline, it's the infrastructure behind it, as well as the data points, that code serves. Itself takes quite a bit of education and evangelism within the folks. I think the other challenge is that you've got people who change roles. The role of a data architect changes, the role of data governance, data steward changes to more towards product thinking. Just applying product thinking is another step. So I would say on the organizational side, the roles, the shift in the roles, the shift in the language, which is the mental shift that you referred to, Kay, is a big one. On the technology side, for organizations that are excited about implementing this, technology, I think I mentioned in the talk, is still fairly awkward. Like if you compare it to microservices, you write a bunch of, Golang, and then you get a Docker image and run it, and it's so good. You already got your APIs exposed, and you've got all of those cross-functional concerns addressed by your service mesh. That we're not there with data mesh. So with data mesh, we're still using whatever technology is out there. The paradigm kind of transcends the existing technology in a way. So where we are implementing this, it's really with, I don't want to scare you off, but it's with blood and sweat and tears, and to create those abstractions that allow you to, deploy a node on the mesh and have all those nice cross-functional capabilities of, seamless APIs to get to it and so on. So be prepared for the amount of engineering that it takes. And if you look at the companies that have similar paradigms applied, they don't call it mesh, and maybe it's not a one-to-one comparison. Spotify is a really good example of those companies. And they do apply, domain kind of thinking. If you just Google their talks, you will see how much investment they've put into all of the infrastructure. That a lot of it is, some of it is open source. To just see this sheer amount of engineering that goes into creating that, wonderful developer experience that you can now, democratize building this data and sharing data. That was a long one.
No, that's really good, and it's obviously an area that requires further time, and I wish we had so much more. I'm afraid we've probably only got one more time for one more question, so I might share a question from Daniel, who asked, Zhamak, that's a really great talk, thank you. Now, when thinking about developing business-driven solutions, an entity can mean different things to different domains. You mentioned that in regards to governance, there needs to be a conversation around parties to come to an agreement and ownership. But I feel that sometimes these differences can't be resolved, or rather the mesh approach can prove difficult in solving business requirements. So this is more a statement of a question, but do you have any comment on this?
Sure, absolutely. I think coming to agreement, and that's why monolithic models maybe in some ways easy because you have one team to decide about everything, about what the model should be, and that team will struggle to serve a lot of different needs. And in fact, the reality is that team diverges from the reality of operational systems. A lot of data scientists, I hear that they go and train their models on the data that's being cleansed and modeled perfectly, and then they go run the model in production, and it just doesn't work because the life has diverged as you move through the pipelines from your operational world. So I do agree that coming to agreement on one big model and one consistent model, whether it's in the form of mesh or monolithic, is a hard task. But what we have learned is that you can be pragmatic as what decisions can be localized and left to the domains and what decisions need to be globalized and we all need to agree on. And yes, there would be entities that crosses boundaries and would require some sort of a harmonization and agreement. For example, again, I would use the example of Spotify, like, track IDs or, artist IDs. Like there are identifiers that's going to be globally unique wherever you go. Actually, in fact, they have to be unique beyond just the analytical data side, because they have to be unique across your operational APIs and analytical APIs, because there's always that cycle that I showed, right? Data flows from operational to analytical and back to operational to your APIs. So pick your battle. A lot of decisions can be localized to the domains to decide what how the facts and reality of the business, the truthfulness of the business can be represented but with local decisions. And maybe there are a few things that would need to be resolved globally. And that's where the platform and automation can, with services and SDKs and so on, libraries and so on, can enforce those global decisions. And maybe let's not use that word, actually. They don't enforce, they facilitate making those, implementing those decisions consistently, providing libraries of types or concerns that are more cross-cutting.
Awesome. Well, thank you so much, Zhamak, for joining us. Really appreciate it. We've got a QR code that'll be splashed up now if you'd like to provide some feedback. But thanks once again, and virtual round of applause to Zhamak. Thank you so much.
My pleasure.
Hello, everyone. My name is Francisco Liwa, and I am a data engineer at Max Kelsen, an ML and AI bespoke consultancy here in Brisbane. I also co-organized the data engineering meetup here in Brisbane. My co-host for today is Leo Horeg. Please introduce yourself, Leo.
Thanks, Francisco. We've got an exciting day ahead of us, don't we? My name's Leo. I'm currently working as a data engineer at the cloud consultancy iTalk in Australia. I spend most of my times around data pipelines and the event streaming space, although I do have a background in machine learning. But that's enough speaker introductions, organizer introductions. Let's move on to our first speaker, Charles Feddersen. Charles Feddersen is a principal program manager for the Azure Synapse Analytics at Microsoft. Charles works with customers globally in support of modernizing their enterprise analytics platform in Azure. Charles will be exploring developing end-to-end analytics solutions with the latest Azure Synapse features. And without further ado, it's my absolute pleasure to introduce Charles.
Hi everyone, my name is Charles Feddersen. I'm one of the program managers on the Synapse engineering team based in Redmond in the US. In the next 25 minutes, I'd like to provide a brief overview of Synapse. We'll look at some of the features, run through some slides for maybe the first 10 to 12 minutes, and then we'll break into a demo and give you a bit of a navigational tour around the studio and some of the key capabilities that are in Synapse Analytics today. Synapse itself is actually comprised of a number of different components. It's a single fully integrated service. When you walk up to the Azure portal, you provision a single service. I think the minimum number of pieces of data you need to put in 8 to provision the service. But it's comprised of a set of capabilities that enable you to build end-to-end analytical solutions. Everything from what you'd be probably most familiar with around those traditional data warehousing workloads, but also complex and very powerful data integration capabilities with support for hybrid data integration from other clouds or on-premises using code-free tools that I'll show you today. We put Spark, Apache Spark, into Synapse as well, so you've got that notebook experience and that engine for running workloads such as the complex transformations, even data science workloads, and really fusing that together with that more traditional SQL-based enterprise warehouse workload. And we encapsulate all of this in a new web-based development studio, and all of this I'll show you in the demo today. Now, if we step forward a little bit, I just talked about some of the core components within the Synapse service itself. Now, Synapse in and of itself is completely open. We support a large set of what we call linked services within Azure as well, where we leverage a lot of the capabilities in other services like Azure Data Share for data sharing, Power BI, and then Azure Machine Learning as well. I'll touch on a little bit in the demo, but also a very broad ecosystem of applications for data integration, data visualization, data modeling, that whole ecosystem of ISV partners. It's a very rich ecosystem, and they all work with Azure Synapse Analytics as well. So Synapse at its core is really enables you to simplify this solution building end to end without needing to go through that complexity of stitching together multiple services repetitively in what was traditionally that foundational analytics component, but then also gives you the hooks and the simplicity to bring in certain capabilities from other Azure services. And like I said, we call those linked services in Synapse. And I'll show you a little bit of that today as well. Now, before we break into the demo, I thought it'd be good to start with the studio and just provide a bit of an overview as to what that actually looks like. When you launch into the studio, you'll see that there's a very simple navigation on the left-hand side: data, develop, orchestrate, then monitor and manage. And this really, as simple as it looks, gives you access to all of your data in a very, very secure and governed manner. If I start by looking at, for example, the Data Hub, what you'll see here is it's a true data lake. Hierarchical files and folders that are accessible not just by the Spark and SQL engines directly within Synapse, but perhaps other analytics engines that you provision in Azure and you want to run a specific workload over that data. But for all of these engines, they can operate over that data in place. There's no need to export the data from one platform to bring it here. Synapse enables you to integrate directly with your data lake, but also blend it with fully managed data, perhaps in a SQL entity, and even write queries that join across both of those. And here you can see in the screenshot exactly what you'd expect from a data lake. Hierarchical file and folder system, of course, this is fully secured through Azure Active Directory as well. For those data warehouse workloads, of course, there's a SQL editor. You can see here actually in the develop layer, it's a bit of a nod to all of the development experiences. You've got not just SQL scripts, but authoring notebooks, code-free data flows for data transformation. You can see some Spark job definitions and even authoring Power BI, which I'll show you shortly. And at the bottom, you can see that we've built IntelliSense into it. Now, Microsoft has always had a very rich set of thick applications, client-side applications like SQL Management Studio, Visual Studio, and Azure Data Studio for cross-plat development. But this web experience is really the most rich SQL editor that we've released, and it's all part of that single Synapse Studio suite of capabilities. I just mentioned notebooks. This is what it actually looks like. So here you can see at the top, I'm connected to one of my Spark pools, as we call it. You can think of it as a cluster, and then you've got a language that you selected. It's a very simple piece of code here that just brings back the top 10 records. But again, it's demonstrating how you've got that full fidelity of development all in a single holistic place, as opposed to jumping between a whole lot of UIs and really a whole lot of cloud services to build an end-to-end solution. Code-free data flows enable you to build transformations where you can source some data, run it through a set of transformations, and then put that into a sink. You might be joining data, and this data could be coming from within Azure, of course. It could be coming from on-premise data centers, and we do that securely through what we call integration runtimes, or even pulling it from other clouds, or actually even just cloud-native applications, like SaaS applications, if you will. And so the power here is that it's completely code-free, as you would expect with an ETL tool. And what we actually do under the covers when you run this is we boil it down and run it on, or still compile it down to Scala actually, and then run it on Spark clusters directly within Synapse. So we think of this as code-free transformation at scale. And for anyone who's sort of built on legacy ETL platforms, perhaps on premises where that was a limiting factor of scale, this gives you the ability to scale these data processing and transformation jobs out without the complexity of figuring out the code for that. But of course, then you can actually augment this and overload it with some of your own code as well. And then I mentioned authoring Power BI as well. And so here you can see an example. The nod to the fact that we're still in Synapse Studio is those icons down the left side, data, develop, orchestrate. But we've taken the web-based experience for authoring Power BI and brought this into Synapse Studio as well. And so here you can imagine that analysts might have done some data manipulation in SQL, maybe data scientists have done some work in Spark, and now they want to visualize these results. You can snap over to Power BI in the same experience, turn that into a rich set of visualizations, and if you just click the little save button in the top right, that'll propagate that to Power BI. And of course, actually Power BI also has a very good integration with Microsoft Teams, which is possibly useful for a lot of the remote work scenarios that we're working through right now. Now, a couple of features that we launched just recently at Build I wanted to spend some time on quickly. One of those is Synapse Link. I spent a lot of time on enterprise data warehouses over the years, and one of the challenges has always been, or I think not so much a challenge, but one of the most mandatory components of that solution was building ETL jobs, building data integration jobs from operational systems and bringing them into the warehouse or the analytics platform. And absolutely, this is still a key component, if you just showed it with the data flows. But in situations where that operational system and the analytics system resides in Azure, we can do actually something a little clever, and we call that Synapse Link. With Synapse Link, we remove the need to build data integration pipelines. Instead, just by selecting a simple checkbox, today in Cosmos DB, you can actually automatically index that operational database into a columnar format without any impact on the operational system, and make it available and kept up to date with latency of around 30 to 60 seconds in Synapse. And so I'll show you what this looks like in a second in the demo, but it's really, really powerful because you can think about having Cosmos DB running an operational system and really high throughput and low latency, and exactly what that platform's built for. And by simply enabling a checkbox in the Azure portal, a few minutes later, that data is indexed, is in a columnar format, it appears in the Synapse Studio. There was no impact to that operational system in running that indexing. And then we automatically keep it up to date, all inserts, update, deletes, all changing data. And you've effectively got this source of real-time operational data directly available in Synapse, where you've also got your enterprise data warehouses, your data lakes, and any other data that you might be doing analysis over in the system. So it really simplifies that integration and that timeliness, the timely delivery of operational data. Something else we talked about was lighting up the predict keyword function in the SQL engine of Synapse. What this really solves is that the long-standing challenge of operationalizing machine learning models where the data lives and providing that scalability of effectively in-engine scoring without taking a dependency on external services, perhaps through your REST APIs where you need to pass records out to score them, which is going to have some scalability challenges with the response rates and latency you would expect from an enterprise data warehouse. The way we implement this is we use the ONNX runtime. ONNX stands for Open Neural Network Exchange. It's sort of, think of it as like an industry standard representation of ML models. And it actually does a couple of things. First of all, I mentioned we run the ONNX runtime in engine, so you get the scalability as the cluster sizes change. But the other nice thing about standardizing here is that if you look to the left around that create models box, there's a whole lot of applications. SAS is actually another application that's not reflected here that can produce and convert either natively or convert models to the ONNX runtime. You know, for data scientists, they'll often use the tool of choice. It might be a tool they're familiar with. And although Spark itself can also produce the ONNX runtime, there are other applications that might be in use. By using ONNX, we effectively enable this common interface that a multitude of different applications could be used, produce a model in a standard format that we can then operationalize securely with all of the governance and rigor in our enterprise data warehouse and invoke that model co-located with our data in the data warehouse. And then by putting it into SQL, which is really probably the most ubiquitous language for analytics, it makes it very approachable for anyone to leverage that model. And I'll show you actually in the demo how we can take that one step further and put this under a database view and completely abstract from the user the fact that there's any predictive analytics or scoring going on in their SQL query at all. So with that, let's perhaps flip over to the demo and I'll start to make some of this real. So here we are in my build workspace now. And as you can see on the left-hand side, everything that we just looked at in the slide. So data, develop, orchestrate, monitor, and manage. And so I'm going to start the data blade here. And what you're going to see is I've got my storage accounts here. So these are all of my data lakes. I can bring this open to show that I've got some Parquet data available to me here. And then down here, you can see I've also got Cosmos DB. I'm going to come back to this one in a second. The first thing I'd like to point out is I can right click on a Parquet file and I get a set of navigations or a submenu here that I can launch a whole set of different analytical experiences. I could go directly into a new SQL script. I could launch a new notebook. I could create a new code-free data flow of this, or I could spin it into a reusable data set as well. And so, for example, if I took the SQL, I could say select top 100 and I launch a new tabbed experience where I by default connect to SQL on demand, which is the pay-per query form factor within. So that's great for data lake exploration, those relatively ad hoc scenarios over the lake. Also really good for doing conversions in the lake. If you've got files that are landing as delimited and you want to convert them to Parquet, it's really easy to do that in SQL, in SQL on demand as well. But if I come back to raw files, the thing I want you to remember is those top 4 elements. I'm in my data lake and I can launch a set of analytics experiences. At the moment, I'm on my linked services, but if I come back to my native workspace where all my enterprise data warehouses are, I'm just going to open this predict DW data warehouse, which we're going to use a little later for another demo as well. And when my tables expand here, I'm just going to take any one of these. Let's take trips 100,000. And what you'll see here is I've got parity. New SQL script, new notebook, data flow, and data set, the exact same as the submenu. And so this is where we're really sort of creating that or blurring that separation between the data warehouse and the data lake. And what's interesting here is if you think about how you may have done this in data warehousing previously, those tools were very SQL focused. That was the nature of the workload. But in this scenario, if I'm a data scientist and I want to launch from my data warehouse directly into a notebook, that's no problem. I'm selecting directly off a table in my data warehouse. I can load that to a data frame. We do a little bit of code gen. I can run that cell and I'm off and running. And so a really efficient way and no need for it to have a separate services for each of these capabilities where you may be moving data back and forth or moving it to a data lake simply for synchronizing between platforms. I'm going to close that one. Now let me come back to where I was in my linked services, and you can see I've got a couple of other things. Here's my Cosmos DB. The little icon down here is the giveaway. So imagine on the back end, I've got Cosmos DB running and perhaps it's powering a website application or something of that scale and that very low latency that Cosmos is known for. Here, this data is going to be only seconds out of date and continually kept up to date as changes are happening in the operational system. I've not built any pipelines. Synapse Link is doing everything for me under the covers to maintain this for me. I can expand this out. And if I click here and select new notebook, you can see I've also got some choices. And so I'm going to take new data frame here. And again, you'll see, let's close that out, that we can launch directly into a Spark experience. And if I was to start then iterating over this code, you can see we've got a native format called cosmos.all. And I could run this and it's going to pull, like I said, data that's only very recent. And if I'm using Spark for machine learning, this becomes kind of interesting because now I've got data that's automatically being kept up to date under the covers for me. I can train and then potentially subsequently retrain my model over the freshest data, maybe even multiple times a day, and very easily operationalize that in Synapse, as I'm going to show you shortly. Let's close that one and now flip over to the develop side. So we've got a set of scripts that we built already. I'm not going to have time to get through all of these today, but there was a couple of things that I wanted to showcase in particular. The first is around the predicting engine scoring. And so here you can see I've actually got a table that's got my model in it. And let me just close this so we've got a little more room to see the code here. And I have a table called trips. The trips table has about 4,500 records in it. I can just run this quickly. I'll show you the messages, 4,655 records in that table. And what you can see here is that there are 7 columns, vendor ID through day of hour, or should be probably hour of day. I need to go change that. Let me scroll down a bit and show you what I did here in this next query. This query is actually going to select the top 10 from that table. And I've added a total amount column, which you don't see here. And that's because total amount is going to take an ONNX format model from the models table. It's going to plug into it the 7 columns from trips right here. And it says the predicted column, the score coming out of that model, is going to be called total amount. And I can go run this. And what you're going to see, it comes back very, very quickly. And this total amount, this is actually a predicted value. So this is not too bad. This is pretty simple and pretty approachable for SQL developers. Now, if I scroll down a little further, however, let me show you how this scales. So here I've got a query that does a few different things. First of all, I'm using predict again. I'm passing in the same model. But taxi trips here, 5 million. This is a table with 5 million records in it. And I'm running a relatively small cluster. I think it's about 1,500 units in size, so not large at all. But what you can see here is when this column comes back, I'm then also doing some work with SQL. I'm going to put a SQL average on it. Then I've got an outer query here, which is actually putting a windowing aggregate rank over that trip amount as well. And then I'm grouping it by the passenger count and ordering by the passenger count as well, or passenger count, trip account as well, right here. So let me go run this. Oops, lost it there for a sec. I'll run that. And so here we're running our prediction over 5 million records and rolling it up. Now you've got there are 2 ways you could do this. You could aggregate the data first and then score it, or you can score it first and then aggregate it. And you would get slightly different results, of course, for each, and maybe different ones are applicable. But what you've seen here is that in 12 seconds, I've been able to go and run a score against 5 million records. So 5 million individual predictions, 1 per record. And then I just rolled it up into this average here. And you can see my stack rank on average trip amount showed that this here must be in a descending order. This must be my most expensive average trip amount. So again, really simple way to not just get access to running the ONNX model through the predict keyword in SQL, but also with fantastic scalability that I can run 5 million predictions in just 12 seconds. But let's take this one step further. What I did then is I went and created a database view. And so here I didn't do any aggregates or anything. I just said, I want to create a view over basically that first query that I showed with the 8 columns, plugging in the predictive model over those taxi trips of 5 million records. What this means then is now I can just run select top 10 over this view. So let's run that. Without any dependency on the keyword predict, I can now bring predictions directly into my data. And this is powerful because now we've basically democratized predictive analytics to any BI tool or any user who understands basic SQL. Right? It's fair enough that people may not understand the nuances of the predict keyword. It's not particularly mainstream SQL, and maybe we wouldn't expect our analysts to nail that. But now you can actually just put it under database view, and except for the fact that you would need to tell them, there's actually no awareness at all that a database view is being deployed here, or a predictive algorithm, I should say, is being deployed to generate this value. Now, if you think about operationalizing them, how can we bring all of this together? So for that, I'm going to jump down into Orchestrate, and I have some pipelines here. And here I've actually got a hybrid file copy that I started earlier. But let's imagine actually, I'll move that down, that I wanted to actually operationalize that. I wanted to bring some data in, and perhaps I'm copying data from one of my source systems. And then I've also got this real-time data through Synapse Link that's coming in. And actually periodically, perhaps every time on a schedule, or maybe when a separate file lands, I want to go on operation. I want to retrain this model. Super simple. First of all, I can just bring out my Synapse notebook. I won't go through the intricacies of wiring up exactly the predictive notebook, but you can see how that would happen right here. And then actually what I need to do is run a SQL store procedure to initialize that model into my data warehouse. Also very simple. We'll put that there and drag the arrow here. Now I could go ahead and schedule this by adding a new trigger. I could click new, and maybe I schedule this on a periodic basis. I could use a tumbling window. If I had files just continuously landing into my data lake, I could use event-based notifications as well. So when that file lands, this whole workflow will load. And this is not just loading directly into the warehouse, but it could be a complex orchestration that does a number of things, such as retraining models in Synapse, initializing them. Maybe we're calling out to Azure Functions for something else as well. But I could run all of that. I won't do it right now in Synapse as well. Set this up to run. And then automatically that Synapse Link data is flowing through. Maybe I'm updating my ML model in the database 4 or 5 times a day. It doesn't really matter, because for my developers, all they're seeing is this database view that I showed at the bottom. And the model's just a new updated model's being pushed in consistently under the covers. And so you can see how this really simplifies that operationalization of ML models built on Spark or other applications perhaps, with that real-time data from Cosmos DB, or perhaps other sources that I've pulled in through my code-free pipelines. So to close with that, I should show code-free pipelines just quickly. If I come back over here, you can see I've got some code-free pipelines that we've used previously. Here's one that's a little more complicated than we showed on the side. We've got some raw customer data. We're doing a join here and an aggregate. If I want to add a new source to this pipeline, who knows where it's coming from, I can select new right here, and you can see a whole set of sources that are probably pretty familiar. There's a lot of Azure sources, there's other clouds, other database technology, FTP as well. So a whole range that you can bring and implement into your code-free pipelines. And then finally, I mentioned that you can author all of the outcomes from this with Power BI. And so I've got a report for Power BI right here. And here's just one example that we built earlier. I'll just close out some of these to give it a little bit more real estate. And all of this can be built on the ML that I produced with Spark, operationalized through SQL to produce a rich dashboard that I can publish out to Power BI. So that's probably everything we've got time to demo today. I'll just move this back over here. And perhaps at this point, we can wrap up and take some questions. Thank you very much for your time.
Thanks, Charles. What an incredible demonstration of Azure Synapse it is. It's really an all-encompassing end-to-end solution with all those integrations.
Yeah, thanks, Charles. That was a great demonstration. Let's move on to some of the questions. The one I had, first of all, was, given we have data sourced from a lot of areas and a lot of different services, how does Azure Synapse Analytics manage the security and governance around and what are some of the best practices?
Yeah, I think so. The security story in Synapse is pretty complete. We think of it, it's twofold. You can think of it sort of top to bottom through the data, and then you can think of it sort of left to right across the compute engines. In the demo, we talked mainly about SQL, but it extends to Apache Spark. Everything coming in the front door is Azure Active Directory. So it's that enterprise authentication, MFA as well is supported. And then on the data itself, when you look at sort of the database tables, we can do incredibly fine-grained data security native column and row level security effectively enables cell level security on the table themselves. It's probably not super practical, but functionally it's achievable to go down to a single cell. There's also dynamic data masking as well on the data, where you can take sensitive data that someone may need to see the actual value, but someone else with a different security context will run that query and see something a little different. And so the benefit of having that security on the tables is it's an enabler for democratization. It means that you can take a given dashboard that everyone in the organization shares with a given SQL query under it. It's the same query for absolutely everybody, but when they run that, their context, their security context on the data could bring back different results. And that ability to do that data security on the data itself, as opposed to a security abstraction layer like views, makes it far easier to democratize this data. And then over on the data lake, everything's POSIX based through file and folder access through Active Directory as well.
All right, thank you for that, Charles. So now we have a question from YouTube, from Maisam Lakhani. So the question is, does Synapse Link support SQL Server, or is it just Cosmos DB?
Sure. Yeah, it's a good question. It's a question we get a lot, actually. So today it only supports Cosmos DB, but we've got intent to light up a SQL database in the future as well. So stay tuned for that one.
Thanks, Charles. We will have a QR code coming up now. If you'd like to rate Charles' talk, please scan it and fill out the survey. All right, let's move on to our next speaker. It's an absolute pleasure to introduce Dom Coiler. Dom is a passionate cloud data architect at Fivetran. He has an exciting talk today about building a code-generated data platform. Over to you, Dom.
Welcome to the Data Engineering Conference Australia. My name's Dom Collier. I'm going to be your host for this talk about building a code-generated data platform. I'm a sales engineer at Fivetran here in Sydney, and my background for the last 7 or 8 years has been in building data warehouses on-prem and also in the cloud more recently. So this talk is really going to be pointed at data engineers, ETL developers or business analysts, and really anyone who's involved with building data structures for BI or ML reporting needs. So let's just jump in. A little bit of context around today's talk, and it's going to be about the modern data stack and how we streamline and automate as much of the modern data stack as we can. So the modern data stack is a best of breed approach to build a modular, agile, and reliable data platform, and it generally consists of 3 parts. We have a cloud-native ELT tool such as Fivetran to land all our data reliably and consistently. A powerful cloud data warehouse such as Snowflake, Databricks, BigQuery, or Redshift. And an interactive BI tool to surface the insights that we're going to pull from that data. So as I said, we're going to talk about automating all these 3 pieces of the puzzle and really the common data foundations that we see inside of these data warehouses. So from building data warehouses myself and being involved with a lot of them, I've really found that there's generally a few common layers, and that's a landing or staging area where we land all the data raw. A history or time series layer, where we persist the data and the evolution of that data over time. And then a modeling or reporting layer, and this is where we have our Kimball, our Data Vault, 3NF, or whatever reporting structures we need for our downstream processes. So as I said, these structures become very common and repeatable across industries and technology stacks. And therefore, we can clearly define a set of structures and rules around these layers. And that lets us build code automation to manipulate those structures and rules. Now, why do we want to use code automation and what's the point of it rather than just building it out by hand? And it's because these become complex and tricky environments to work in. And as you can see here, our data engineers are generally available from getting that data from source to our data warehouse and maintaining those pipelines. And then our data analysts for building those curated data models and surfacing those insights, the reports for our business users. And each of those take time by themselves. And then eventually we end up going back to data sources, either with new data sources or to get more data. And our engineers follow the same loop, and our analysts, again, go through the same loop. And this quickly balloons out to weeks or months for these constantly evolving data warehouses. So why we're trying to build those common data platforms, and then why we should use automation, because I believe these become repeatable and standardized processes that we can put in place to help us build these out. And the benefits of automation are really around the speed and the agility get greatly increased, and we have a smaller delivery cycle on our data platforms. We get inbuilt governance and controls, such as standardized naming conventions and data types. Lineage and metadata gets built in, so we know where the data came from, who's touched it, at what time, and what it's done, whether it was an insert, update, or a delete. Our code logic becomes standardized and reproducible at scale across all layers of our platform. This then unlocks standardized workflows, and the movement of data becomes standardized, so we know what everything's doing is playing by the same rules. We reduce human error in terms of copy and paste errors. We start to unlock CI and CD workflows inside of our data platforms as well. And we've probably all built a fair few of these, and let's be honest, this is a bit more fun. It gives it a new flavor into our projects. So what do we need for code automation and to automate this modern data stack? It boils down to three main things. We need metadata, or source to target mappings. And this is what tables we're going to move, what columns inside those tables, the data types, what primary keys we have, and other associated metadata around that. We need data structures. So automation is definitely easy when we have one-to-one relationships between those tables. But all our structures need to be clearly defined and adhere to naming conventions, because we're probably going to reference tables in the code or objects in the code that aren't actually built yet. And the third, we need code patterns. And these are really the templates we're going to apply when we're doing the automation. And these can be upserts, they can be deletes, they can be merges, and then right up into our dimensions, facts, hub links and sats, or whatever we're building downstream. That'll be the patterns that we're going to apply. So the solution, as I said, I believe, is to automate this. And automating two ways. Fivetran is going to automate the ingestion of data for us. So it's a plug and play as you go ELT tool, and lands all that data in our database for us. And then once we've landed that data in our staging layer, that unlocks an information schema. And essentially that's the first part of our source to target mappings. I will say, obviously, Fivetran is a great tool, but if you're not using it and you're using any other ELT tool, once you land that data, you're still going to have the information schema. So this is completely dependent from here on out, as long as we get an information schema. And then what I've built here is a few views, and this is where the automation is going to happen. So we're going to automate structures off that metadata, and that's going to be a staging view, and that's going to give us some governance lineage and unlock a CDC mechanism. We're going to have a history table, and that's where we're going to store and persist this data and its evolution over time. And then these two here are our patterns. So we're going to have an insert and a merge pattern, and the insert's going to move the data into our history table, and the merge is going to update the is current rows and the non-current rows, so we keep track of those. On top of that, we're going to have a history layer with the current records only for kind of ODS and BI purposes. And then we'll have the history table, which will have all the evolution of that data. So let's jump into a demo. Let's have a look what it looks like. And all the code I'm going to show you now is available on my GitHub link that you have here. So let's jump right into that demo. And this is Fivetran. Fivetran is an ELT data pipeline as a service product. It needs a destination, and as we saw in our architecture, we're going to use Snowflake for this demo, and I've authenticated into a Snowflake instance now. And we're going to quickly set up a connector. So we're going to use a SQL Server for this instance. And we're going to give it a schema name. And this is what it's going to be called inside our Snowflake database. Let me just connect up here with our username and passwords and our sales database. So while this is running some connection tests, as I said, Fivetran is a ELT data pipeline as a service. Now we use databases as a service, such as a Snowflake. So why not use a pipeline as a service tool as well? And what Fivetran is really good at is connecting to all your data silos and centralizing those in a cloud data warehouse for you. It has a multitude of connectors. Let me just select this certificate. It has a multitude of connectors across 4 main areas, and that is applications, so things like your Salesforce, your Adobe, Google, and Facebook analytics and ads, your Marketos, and your NetSuites, and your Shopify's, things like that. It connects to most databases, such as SQL servers, Postgres, MySQLs, and Oracles. And then it connects us to file storage. So Azure S3 or Google Cloud Storage and most of the other flavors of cloud storage that you can think of. Fivetran will connect to, and it will pull all that data out and load it into a destination for you. Now, what's good about Fivetran is it is a set and forget model. So once you connect those connectors up, Fivetran will handle everything else. It'll load all your historical data, and it will do all your schema detection for you, so your pipelines will never break. It'll automatically add columns and new tables when they get added, and keep the pipeline up to date so that data is always flowing. And that's going to be our first layer of automation. So we're going to use this to automate all our work, which will generally take us weeks to months to land all that data inside our Snowflake database. So you can see here, I'm going to review the schema. And this is where we can select which data we want to pull from that source. So this lets you deselect and select columns, and also lets you go right down into, tables, and right down into a column level. So I'm going to take off this test table, and I'm going to bring through these 3 tables here. Once that's done, obviously you can see we have some nice status pages and user actions, but for this demo, let's just start that sync and jump into the automation platform. So as we can see here now, I've got a little database here. We've got our code generation platform, but we have no schemas now. So soon that orders schema is going to pop up from Fivetran and populate those tables for us. So while we're waiting for that, to reiterate what we saw in the slides, we're going to build some DDLs via code automation. So we're going to build some staging views, and they're going to sit on top of our Fivetran tables for some governance and some lineage and a CDC mechanism. We'll have a history table, which will be a one-to-one relationship with those views, as we said, very important for automation. We'll have some history views on top of those tables, and this is really optional just to speed up the analytics and give us a current record view of our data. And then we're going to have inserts and merges, and these are our patterns. This is a code pattern we're going to apply to move the data. Obviously, new rows will be inserted, and then we'll merge in the updated rows so we can keep the history of that data. And this is what they look like. So obviously, there's a bunch of views there, and these is a view of one of those views. So you can see here, it uses the information schema. So essentially, no matter what you put in, whether you use Fivetran to load your data or another tool, you will still have this information schema. So this platform will still work from here on out to keep that modularization and 3-tier architecture nice and separate from each other. So we have the information schema, and then we're just going to use some concatenate statements to punch out these DDLs. The main kind of one here that you probably might not have seen before is this array ag. So we're going to make an array of the column names, and this is one of the main drivers of the platform. You can see here it's used again over and over. This one's going to produce an ETL hash, very important for our change data mechanism to be able to capture what's changed when our data comes through. So let's refresh this. Hopefully Fivetran, and it has landed our orders table, our orders schema and some tables for us. So now we can run this. As I said, we've got an information schema. We need some structures, which was our second principle. And you can see here, it's going to push out a create view statement, selecting all our column names. And here you can see we're going to build that hash, very important for our downstream process. So I'm going to copy this data, these DDLs. And we're going to run these 3. And there we go. We've created 3 staging views. After that, like I said, we're going to create history tables as well. And you can see here, very similar setup using the same array of column names. We're going to do some data type mapping here for some standardization. And in this level, we're going to put our governance columns on. So we're going to know where the data came from. We're going to have an execution date time of when we moved it, what change type we had. So an insert, update, or a delete. Our important row hash, and then our CDC 2 columns of is current and our expiry date. So similar again, now we've got our information schema. We can just select these, and you can see here it's doing a create table statement this time rather than a create view statement. So again, we're going to grab those, and let's run those 3. And before I do that, I always forget we need to create our schema. Cube. And let's create those 3 history tables. Similarly, again, we're going to create the history views, and this is just a view on top of those table where our is current is Y. So this is for our OD operational data store type workflows. And if we're not worried about the is current kind of, the history of our data in certain analytical reporting. So a nice to have and an optional. If you don't want to use it, then obviously you don't need to build this piece. Cool, so let's refresh and have a quick look. And we should have our landing layer here from Fivetran, very nice. We've got our views to get our CDC mechanism on top. We've got our history tables, and you can see here a one-to-one with a nice scheme name persisted through and a solid naming convention, and our views on top of that. So then we'll jump over, and now we can use our third principle of automation, which is our code pattern. So again, as I said, we've got our information schema, and we've got our structures. The third piece is our code pattern, and then as you can see here, we're going to do an insert pattern. And we're going to wrap this in a Snowflake task. So this is how we can then orchestrate this for later on using a nice cron schedule or anything else that's going to kick off a task for us. Very similar again to produce a DDL. And again, for those tasks, so we're going to have a batch. We're going to have 1 batch per schema that we see. So I'm just going to quickly create a master task, and this will be the hierarchy of our tasks. So let's run this. And again, you see a very similar workflow is happening now. Let's grab one of these open and have a quick look. And as you can see here, so we're going to create tasks. We're going to align them after the batch task runs, so we can only schedule the top tasks. Doing an insert statement, and we're selecting everything from our staging view. We're doing some change data capture here for governance and lineage, and we're going to have this is current column for Y and P, and we'll get to the Y and P in a minute. Select everything from the staging, join that to our history view on our current record, and this is our CDC mechanism, nice and simple. If that join on the business key doesn't yield a result in the history table, then we know it's a new row because we haven't seen it before. Or if those ETL hashes that we created in our staging layer are different and we get a join, that we know it's an updated row. If we join and the hashes aren't different, then we know it's the same row, it hasn't changed, so we can exclude it. So I'm going to run one of these just so we move some data across. And we can see here we've moved 10 rows. And then I will create the rest of these tasks for I look at the end. So again, you can wrap these into your CI/CD processes, so all these scripts get executed and you don't have to copy and paste and run through them like we are in the demo. But we're doing this just to see how it's going to work. Great, so we've created our tasks, and then if we jump in here, we have a look at show tasks. We can see we've got our batch task and our 3 insert statements underneath, and we've got some data in our history table. We can see we've got expiry date, nothing's expired yet. We've got our row hash, everything's been an insert. We know where it's come from, and we know what date we've got, and everything is current. So before we run the next one, I'm going to run some data. So we're going to insert and update some data into those tables. Perfect. Let me just make sure those updates ran. Okay, so now we've got some changed data. Fivetran will have finished its historical sync. And we're going to fire Fivetran off again. And we can see we've got some nice statuses here that our historical syncs are finished. So while that's running, like I said, we're going to merge in our changes once we get some in a second here. So how that merge task looks, let's have a go. Very similar again, information schema, pushing out a DDL. And this is the more complicated of the two patterns that we're going to see today. So if we grab this merge statement out, we can see here, we're going to create a task for the merge and we're going to assign it after our insert task. Very important, our naming standards here to make sure all these link up properly across all our hundreds or thousands or how many tables we're going to build. So we're going to merge here and we're going to see we're joining the history table on top of each other for the current record and our pending records. Now, if you remember, we inserted new records as current because we know they're new records, but our updated records, we insert them as a P, and then we'll go back through here and then make sure that we archive or expire the old record and change the new record to Y. So as you can see here, we're doing that down here. If we do match and we get a P, then let's update it, make it a Y and a current record. When we match the old record and it's Y, then let's expire those records. So we're going to change them to not current. We're going to put an expiry date in, obviously update the timestamp and change the ETL type that we have changed it. So let's go ahead and build these merge statements as well. Copy those out and run them again. Perfect. Let's check Fivetran. Hopefully it's finished loading those few rows through for us. And it has. So as you saw before, we had 10 rows in our column, in our table, sorry. We're going to add 3 more and we're going to update a couple of those as well. So let's run our insert task again. Let me just grab it back out. Okay, you can see we've added 5. So the 3 new columns and the 2 updates as expected. And if we have a check in here again, we can see now we've got 2 pendings and the 3 new columns have flowed through. So now we need to run our merge. These should update to IDs number 1 and 2. These will update to current, and obviously number 1 and 2 here have been updated, and we're going to expire those and make them not current. So if we go back to our merge statement and let's run our merge. Okay, let's go back and have another look. So perfect, we can see we've got 2 expired rows with expired date times because they're the 2 updates we've done, and those same IDs now have new current rows. Perfect for historical layout. We've got some data evolution happening here. So great for data scientists now who want to see how this data evolves over time, and obviously a lot of BI use cases also want to see this. If we don't and we still want to do ODS right now, maybe we only want to look at this history later. If we look at the view of the history table, we are only getting those current records. So if we want those, we can hit this directly and go straight out. If we look at our tasks again now, if I'm in the right schema, if we look at those tasks again, we can see we have all those tasks wrapped up for us. All our merge and inserts wrapped into our batch. So now all we need to do, as you can see here, I've scheduled this to run every hour. Fivetran's going to land our data for us. This is going to run every hour, insert and merge it into our history layer. And we have a data platform built in a space of a demo. Hopefully you can see how that's going to spawn out into the wider data platform now if we're doing hundreds of tables at a time. Obviously you can wrap these into a stored procedure or any other code you have, so these scripts fire by themselves. And this is where we really get into that standardized data platform. So we have standardized lineage, we have standardized code that we know every table is doing the same thing. We have standardized naming conventions and standardized data types. So we have a very good foundation now that we can put some reporting views directly on top of this and really just get straight into the business rules and start servicing some reports. So we have, I guess in this day and age, intelligent systems and intelligent applications. And my challenge or question is, why can we not have an intelligent database that can organically grow, it can update itself, and it can really just unlock the potential of these databases and free up our time for doing these mundane tasks. Thank you very much for listening in. And as I said, all this code is available in my GitHub repository. Thank you very much.
Thanks, Dom. That was very good presentation. I've used Fivetran myself, and it's really useful. Now let's go to the Q&A. We have some questions here from Slack. From Sid Singh, his question is, how does Fivetran handle data deltas from source?
Thanks, Francisco. That's a great question. And Fivetran encapsulates all the delta mechanisms from source. We do a lot of work with our vendors for our SaaS applications to pull those deltas out for you so you don't have to worry about it. If we're talking about database connectors, then we do log-based replication and use any of the mechanisms native to those databases.
Awesome. Takes a lot of the work out of our hands. I had another question. So I know Fivetran has a giant list of connectors. If we want to ingest data from a source that Fivetran currently doesn't support, do we have any options around it?
Yeah, we sure do. And as you said, Fivetran's value add is bringing those 200 plus connectors to really streamline those ELT processes. But if there is one that we don't support, definitely let us know, because we're always trying to add to our connector list. We have a few options. We support cloud functions such as AWS Lambda, Azure Functions, and Google Functions. And we can really split that process in two, where you can write essentially your own function to hit an API or a source. And Fivetran will call your function and take over the landing and the schema updates of that data into your destination for you. That's one way. If it's not an API and it's maybe a bit more of a legacy system, we can do CSV exports to a blob storage or an S3 bucket, and Fivetran can consume the data from there with all the good delta and resiliency that Fivetran brings.
Awesome. Good to see we have lots of options. We'll take one more question. This one was from YouTube, but how does Fivetran handle a scenario where a column is added to a source table, but the load method to the target table is incremental? Will it update the schema of the target table? And that's from Michael Flisowski.
Yeah, great question, Michael. And it doesn't matter that we're doing incremental updates. We'll recognize there's been a schemas change on the source. And as you said, we'll definitely add that column or update that column's data type in your destination, automatically amend the data pipeline, and just continue landing that data in the delta down, and pull any historical data if there's some added to that column back in time as well. So completely encapsulated and fully managed for you in that scenario.
Awesome. Appears to take, a lot of the work out of our hands and make things easy. So we'll have a QR code coming up now. And that will, if you want to rate Dom's talk, go ahead and scan it. Dom's also available in Slack. If you have any further questions, please send them through. The QR code will come up now.
Experience fixing data pipelines with schema mismatch, errors, such a nightmare, right? Well, our next speaker, Vidya, will walk us through how we can manage an ever-changing data model. She is currently a software engineer at Vanguard Australia, and she's also the founder of the KafkaNerd.io. Let's welcome Vidya Venugopal.
Hello everyone, my name is Vidya. Today I'm going to be talking all about schemas. I'll start off with the importance or the benefits of having schemas in place, and I'll also get more into the way the schemas are currently being used. So a little bit more about myself. I currently work with Vanguard Australia, and my background has been mainly on enterprise integration platforms and distributed systems. These days, I've been spending a lot of time on event streaming, and I've also created the KafkaNerd.io, where I share my thoughts on Kafka. So this is what I'm going to be covering today, mainly what is the actual need for schemas, and then I'll get more into the way the schema has been managed in the web services world and event-driven world. And I'll be talking a bit more on the event streaming, and we'll see how complex it is to have a system in place to manage the schemas. So starting with the actual problem space, what is the need for schemas? So let's assume we have a service that's exposed to a customer to place the order. And we know that in any enterprise, we always have the need for different services coming along. So in the same way, let's imagine a service B comes along. And in this scenario, maybe the analytics team wants the data from service A to generate a report. And we have the service A communicating with service B, the kind of the data that they're going to receive. So all good here. Now comes the scenario where service A realizes the need for another field key D, and in this scenario it may not impact service B, and service B might ignore this field, or they might just implement the changes to use this field. Then service A makes another change. They remove the key C, and now we can see that the service B is broken. So now we'll have people from the developers from service B kind of debugging to find out what went wrong and talking to service A to understand why they had to remove this field. And sometimes I've seen the service A going back and reverting the changes, or sometimes service B surrender to this and they might just go and make the change, and service B is all up back again. Now in this way, we know that in any place, we'll always have the need for many more services, and in the same way, let's imagine another service, maybe a shipping service, C comes along. So in any of these breaking changes like this, we are having two different services broken now, and we'll have people from these two services trying to figure out what went wrong and talking to service A to figure out what is the real need for taking this field off, and they'll work towards getting this fixed. So in any enterprise, we have a lot of services relying on the data from a service, and in this kind of world, if we don't have a way to communicate the changes, we will always end up in a way like this. So that's when we realized the need for schemas, and here comes the schemas to our rescue. So let's look back at the same example that we were talking, where we have service A and service B. Now we want the data being communicated, and here we introduce the schema or contract in between. Now service A says this is the contract, and you can expect the data based on this contract, and all good. Service B exactly knows what to expect, and they can have validation and certain things on that. Now let's look at some of the examples of the schema. So one of the example is like a XST that we have here. We have three different fields, and when the payload comes along, you know what exactly to expect. You want a first name with which is a string, last name string, and age in an integer. And the same way you have a JSON schema as well, so depending on a JSON payload. And now having a contract in place enables us to have versioning. So suppose we have a scenario where service B, like how we said earlier, service B could be the analytics team, where they say, we are good with the version that we are using now, and then shipping service C comes along and says, it'll be good if we can get one more field, or this data will be useful for us. And in that case, service A can say, okay, maybe I can expose both version 1.0 and 1.1 so that consumers who have a different pace can still have the data accessed. So this way we realized the benefit of having schemas or contracts in place between services. So this definitely improves the data quality, and this enabled us to have versioning. And we are able to see that schema or contract is the best way to even document your interfaces. So even before you start the implementation, or if you want to share with the consumer services, or even before they start making the changes to incorporate these new contract changes, it's always a way they can see what they're going to deal with. Now the last one is it enables contract testing. So contract testing is not a new concept, but I think these days we are more conscious about contract testing, and I'll talk about it in my upcoming slides. So let's see how schemas are being used in the world of web services. So if you see here, we have service A, and it could be either a SOAP or a REST service, and in the same way we have either a XST or a JSON schema being used. And if you look at the SOAP web service, this is the way we used to always go about with a WSDL first approach, where we define the operations, the schemas, and some of the security aspects, and everything being documented and specified upfront in the WSDL, and we used to generate code out of this. And the same way for the REST services as well. If you see, I've seen these days everybody relies on a schema first approach, and we have been completely relying on the API specification languages like OpenAPI and RAML. And if you see here, the way we have having the API specification, it's more like we know what to expect from different endpoints, what data is going to be exposed, and how it's going to behave in different scenarios, what are the responses, what are the response code you can get. And so these kind of aspects, and we have been completely relying on some of the tools, the Swagger tools like the editor, code generator, validator, and most of the things to support this kind of an approach. So this is one of the another example I just found on open banking. So if I just want to go about and start using this, I know exactly what to expect. So this is like we have found this works better when we have the schema being defined first. Now let's get into the aspect of once the schema has been defined, so contract is in place. So when any changes happen to the contract, we usually pass that on to the consumer service, and consumer service starts the implementation based on that contract. And then once we have all the integration tests written for the implementation, what we have done, we ship it to the pipeline, and we'll have all these long integration tests running. But some of the cases we realize later that we find issues much later down the line, and that's when we realize the need for a contract testing much before we even start the implementation. So that's where the contract testing comes into place. So we can see here, initially when the contract is being given or anything changes to the contract, we will have a consumer-driven contract test against this contract mock, and we'll see, what are the changes that's come along, how does it work, what do we expect out of that. If we use only one endpoint, we can just get that tested. So we don't have to go about and do the implementation first, we can just get this tested initially. So one of the examples that I've seen is Pact, and so it's the kind of the way I said earlier, you can have the mock provider, and you can have the consumer. It's mainly like the consumer-driven test against that, and what are your expectations, and does it really cover all your expectations on that perspective. So that's all about contract testing. It'll be good to think about contract testing if you already have the contracts in place. Now let's get more into the event-driven architecture. So in the event-driven architecture, if you see, it has been more asynchronous communication. So we did see the synchronous ways, the way we have been using the APIs, and now from there we are looking at more into where the order has been created and maybe something else need to happen in the background, like maybe this item needs to be shipped, or maybe we need to send the data to the data lake. Any such thing. So something that has triggered, an event came along and that has triggered a number of different things. So it's more asynchronous, and in that world, initially we came up with the queuing, and in the queuing world, it's more like command driven. Maybe service A says, can you go and do this? So in this scenario, service A knows exactly to whom the service A is talking to, and service A would pass on the contract that they are using to service B, and in this scenario, the service B knows exactly what to expect, and service B will also have a few validations being done on that. And if anything goes wrong, in the queuing world, we always put it onto the data layer queue, and we analyze it later, or maybe reprocess it later. So let's look at one of the example here. We have service A and service B, the same scenario, and we have the contract being shared earlier. So that's the order XSD that you can see there. And when the shipping order XML comes along, the service B validates it against the schema that's been provided. And like I said, if it's some other payload, something quite not right when they did a validation against the XSD, then you might just put it onto a data letter queue. That's all for the event-driven side. And now let's see the event streaming. What is event streams? So it's all about capturing all the possible events and having the capability to store them, and having the ability to process them on the fly. So that's what event streams is all about. Let's get a bit more into it. So in the event streams, it's a bit different to the way we have seen with the queuing world, where any consumers come along and they consume the data, and the data is gone from there. So that was the real need for us to actually put it into a data letter queue, because we need to store the data somewhere if something goes wrong. Now, if you look at the way in event streaming, any data that's coming along and comes to the stream or topic, and the data is stored there. So what that means is any number of consumers coming along. Suppose the shipping service comes along and starts reading, consuming from one service, one stream, and then maybe after a while, the analytics, the service B comes along, and it says, I want to read from the beginning. So it's like different consumers can come and get the data in their own pace. And another possibility here is, because you have the data still retained there, if anything goes wrong, you have the capability to replay that. And that's how it's a bit different to the way in the queue aspects to how the event stream is. Now, another aspect is event stream processing. So once you start processing the data from the topic or stream, you can have the capability to analyze them on the go. So these earlier, what we used to do, we used to push through data, and anything we'll push it to the data lake, and we'll have the analytics team finding insights and sharing it. Maybe it might take another 2 days or maybe 1 week to even come out. But now it's more about like we can analyze it on the go, and maybe based on what we found right away, we can trigger another event to do something else. So that's where the processing capability comes in. And some of the good examples of streams are Apache Kafka, AWS Kinesis, Google PubSub. And if you look at the stream processing, we do have Kafka streams, KSQL, Apache Flink, and Apache Beam. So to what we have discussed here on the event streams, where we have different producers and consumers consuming data at different pace, and it could be like data a bit different still existing on that stream. So here we cannot really survive with the kind of the way we have been managing the contract in the event driven, the previous slide that I showed. So that's when the rise of schema registry. So let's look at how the in the world of event streams it's going to look. So if you see where we have the contracts now, it's actually shifted more towards the streams or topic, because it's very hard to maintain this contract with every producer or every consumer. We want it a bit more specific to every topic, where we say anything that comes along needs to be validated. And since we have the data, we might have the data with different schemes at the moment in a topic or stream. It needs to have the capability to kind of, even if they produce with a newer schema, the consumer should be able to read with the older schema. So there are different aspects that we'll have to think about in this space. So let's look at how schema registry works. So in schema registry, when you have a topic, you'll have to register a schema for that particular topic with the schema registry. And every producer that sends the data has to initially get the schema ID and then send that data along with the ID, and the same way with the consumer. So in this way, they will able to be ensure that even though the schema is changed or the schema evolves, we still have some way to figure out the consumers still be able to come and consume the data. So let's look at one of the examples from Kafka, and this is Confluent Kafka schema registry. So in here, if you see, we have the schema registry on top, and there are different data formats it currently supports, and we have the Kafka topic in the middle, where the producer, if it's the first time, it might just go and register it, and it'll get the ID, and along with that, the serialized data has been passed to Kafka. Now, the same way the consumer gets the ID, and it deserializes the data once it consumes. So now, let's see what happens if the schema changes. So that's where in the schema evolution there are different patterns like backward and forward compatibility. So to give a brief about that, let's take an example where we have a schema being defined, and the producer has been using that schema to produce data to the topic, and then later on then there comes a need to make the change to that schema. Maybe we need to add a new field. And what happens if the producers start publishing with this new schema? And so in the topic, we will currently have the data that was published with the old one and the data that's published with the new one. So the consumers, if they're using the old one, they should be able to consume the data the producers have still sent with the new schemas. I'll talk about it a bit more when I'm showing the example. Now, let me show a very simple example here. This is Avro schema, which has just two fields in there, human address and status. So I've just defined the schema initially, and now we can just go about register the schema. I've just used the Confluent schema, the control center, and otherwise you could use the schema registry API, or you could directly, once you produce it, could auto register as well. So let's look at the producer code. That's the parking events topic, and schema registry. I have the local being configured, and the parking address, if you see there, that's being generated from the Avro schemas. And let's see what happens once we send this data. So it's been sent successfully, and it's all good. Now let see what happens if I'm going to go and change the schema. So the scenario that I said earlier, where I add a new field that's parking ID, but I don't have a default value in there. So the by default, you have the backward compatibility being configured. And what happens in this scenario, when the producer produces the data with this new schema and there's no default value in it, the consumer tries to deserialize the data, it doesn't know what to use for that particular field. So that's where then when you have some changes coming along like this, it's very important to think whether it is backward compatible or forward compatible, and you need to have your schema evolution or the schema changes thought upfront. So now in this scenario, like I said, since I don't have the default field, I could directly go and check in the schema registry if it's compatible, or these days I think there is a Maven plugin to do the compatibility check. But here I'm just directly going to send it from my producer, and let's see what happens. So I get a 409 expected. So schema being registered is incompatible with an earlier schema. So like I said earlier, it's when we have any more changes coming along to the schema, it's pretty important to think through this evolution perspective, whether it's backward or forward compatible. So that's all it is. If you look at what we have seen in the schema registry, this is like a golden gateway between the producer, consumer, and the topic. And this way, we are able to have an efficient way to serialize and deserialize the data, and we are also able to have an efficient way to evolve our schemas. That's all was there for me. So we spoke about the benefits or importance of having schemas, and then we looked at the way schemas are being used in the web services and also in the event-driven world. And I did get into the event streaming, and we did see the need for schema registry as well. Like we see here, we are living in a super connected world, and if you think, for example, in any enterprise, we have a lot of connected apps or services. And if we want all of these services to seamlessly work together, and if you want to generate quality data, it's very important to have schemas in place. I hope this session was useful for all of you. I'm happy to take any questions after this, and feel free to reach out to me on LinkedIn or Twitter. Thank you.
Thanks, Vidya. That was great. As data engineers, I'm sure we've all felt the pain of schema management and evolution. You should all know by now how important it is to set up these contractual agreements between different parties. Let's move on to some of the Q&A. One of the first questions I had was, what's the difference between a schema registry and something like a data catalog in AWS Glue?
So to talk about that, I think the schema registry would be more kind of similar to maybe one of the other product that I can take is AWS EventBridge schema registry. So that's something new Amazon has come up with. So that's like a pretty way that we can see there will be more of schema registries and a different ways to manage schema that's going to come along. So we can see that EventBridge kind of works only with Event Bus at this stage, but I'm sure maybe we should be, more different products might be coming along for managing the schema evolution.
Right. Thanks, Vidya. So we've got another question here. So we've mentioned about the Confluence schema registry. Is there any other tooling or services you would recommend?
So my experience is mainly on Kafka, and with Confluence schema registry, with any way that you run Kafka, let's be with the Kafka cluster by itself, or even Insta cluster, or Hortonworks, anything that you use, you can plug the Confluence schema registry. But other than that, You could have maybe build your own schema registry with S3 kind of a system under the hood where you can store, and then you can have the producers and consumers kind of checkpointing against it, and maybe like a caching in your producers and consumers. That might also work. But other than that, I've seen with Apache Pulsar and Solace as well coming with different ways to have this schema management. Like I think Pulsar has a schema registry itself, and Solace a different, kind of like a schema registry, but to a different level. Yeah.
Awesome. So I guess it's more about having the right tool for the job.
Yeah.
So I had one more question. Can you describe use cases for backwards compatibility?
So if you look at any of the enterprises the way we currently have, and anytime you make a change to the producer side, it's kind of thinking across, how the consumers are going to get affected. And sometimes what happens is when you go with a system like Kafka, where it's not just you consume the event right away, it's more like you have the events being persisted there. So you might have the data which was written with the previous version of your schema, and you might have the new version of data as well. So if consumer moved on to the new version, so because it's like you change the schema and consumer move to the new schema, and it can still read data with the previous version. So suppose you added a new field onto the version that you are going to use now, but you added a default value. So when it reads the older version, it can still get it with the like a default value. So it knows to deserialize it with that. So that's kind of like a use case that we usually use.
Yeah, awesome. So yeah, I guess ensuring all that compatibility lines up. Yeah, we'll wrap up your talk now, but we have a QR code coming up shortly. And if you scan that, you'll be able to rate Vidya's talk. Any feedback's really useful. Video will also be available on Slack if there's any further questions. Thank you.
Hi everyone, welcome back to DataEng Bytes, a community-built conference that showcases the best of data engineering right here in Australia and around the world. I found Vidya's talk fascinating. My name is Noel Hansons and I am the Data Engineering Manager at Lifeblood based in Melbourne. I love leading data teams, data communication and data governance. I also run the Data Engineering Meetup here in Melbourne. My co-host is Katie Peterson. Can you please introduce yourself?
Thanks, Noel. Hello everyone. We have a really great afternoon ahead of us. My name is Katie Peterson and I am a software developer with a passion for data from ThoughtWorks based in Sydney, Australia. It is a pleasure to introduce our next speaker, Louis Lee. Louis is passionate about data analytics and associated technologies. He's a member of the sales engineering team in Snowflake, helping customers to find meaningful insights from a vast amount of data that they collect every day. If you do have any questions for Louis, please pop them in the Slack channel. Now let's hand over to Louis, who will be talking about Snowflake Cloud Data Platform, building a governed data lake. Over to you, Louis.
Hello, everyone. Welcome to Data Engineering Conference 2020. Today, my talk is on building a governed data lake using Snowflake Cloud Data Platform. My name is Louis Lee, and I'm a senior sales engineer from Snowflake. It's great to be here today. Before we jump in and start talking about Snowflake, let's level set on the current state of Data Lake and the opportunity it presents. Data Lake represents a major part of how modern companies invest to leverage all their data and build a data-driven culture. But the ROI on data lakes is yet to be fully obtained. In fact, the ROI on data lake has been pretty low. For example, 85% of big data projects fail to move past preliminary stages. 72% of companies admit that they have not forged a data-driven culture, and the reason is not that those organizations have not invested in technology. Quite contrary, we've seen the massive investment made in technologies from Hadoop to cloud solutions, you name it. One of the key reasons data lake projects have not justified its ROI is because of lack of data governance in general. For example, 84% of CEOs worry about the quality of data within their organizations. There's no clear governance.
Hi, everyone. We're experiencing some technical difficulties just for a moment, but we thought we would discuss a couple of questions as we go through. And Katie, I'm interested to hear from you. Over the last 18 months or so, what's the most exciting piece of data engineering technology that you've come across?
Thanks, Noel. Sorry for the technical difficulties. I think I've been working a lot with Airflow recently, which is a super exciting technology. And I think we are back online. So let's hand over back to Louis.
Forged a data-driven culture. And the reason is not that those organizations have not invested in technology. Quite contrary, we've seen the massive investment made in technologies from Hadoop to cloud solutions, you name it. One of the key reasons data lake projects have not justified its ROI is because of lack of data governance in general. For example, 84% of CEOs worry about the quality of data within their organizations. There's no clear governance policy on what good data quality looks like, who owns it, who has access to the right data at the right time, how data lineage is being tracked, and so on. Without these governance policies in place, data lake often end up to be a data swamp and left with undefined data, unusable data. It is estimated that 60 to 73% of all enterprise data actually goes unused for analytics. In particular, even though companies have been treating data lake as endless repositories of data, the result is that they end up hoarding data in data lakes, but without any organization or structure. There is no easy way to make data accessible and put it to use for analytics. Often because someone other than the analyst owns the data and they have to check with them before using it, or no granular access and privacy control available. Meanwhile, query performance is often very limited to concurrency and scalability issues. So analysts often end up with both limited performance for analytics and also large portion of data inaccessible to them in the lake. That's why return on investment on data lake investment is difficult to achieve. Most of the data needs to be transformed before it can be consumed, but data transformation often entails a combination of diverse coding and tooling options to fulfill the needs of different users and use cases. The architecture often ends up to be complex and many pieces of technologies stitched together. As a result, data pipelines tend to break at heavy workload with performance degradation. Last but not least, governance and security. With regulations like GDPR and CCPA, it's really urgent for companies to govern, track, and understand how their data quality is, where their data is used, what has happened to the data, and who has access to it. But it's extremely challenging to have full visibility of that. With data movement comes more uncertainties of security and risks. Organizations have to make the difficult choice between the rigid data architecture with strict security and governance rules and giving agility for more users to leverage data, but not both. While this depiction is not intended to be entirely accurate, it is indicative of many teams like yourself are dealing with a complex web of technologies stitched together to deliver data from its raw source to intended destination. Across the integration, transformation, aggregation, and delivery steps, multiple different tools have been deployed. Each connection point is a possible point of failure. And governance, security, and silo issues are commonplace with this approach, as multiple copies of data eventually emerge to meet the varying needs of different parts of the business. In the end, you spend more time managing infrastructure and little time to actually working with data. In terms of our architecture, this is what a modern data architecture looks like with Snowflake. So on the left are all your data sources in your organization, and it could be hundreds there. Structured, semi-structured, all would feed into Snowflake because Snowflake can natively ingest semi-structured data without pre-processing it. We work with any ETL, ELT tools on the marketplace. You can stream data, you can batch it in, and there are many ways to get data into Snowflake. And once it lands in Snowflake, there's only one single copy of data, and you have a choice to run on the cloud of your choice. We are cross-cloud as well, so you can set us up to be replication failover across different regions and even different cloud providers, just in case there is a global outage on one of the big 3 cloud vendors. We can use Snowflake as a data warehouse or as a data lake. We can run data science workloads. We can simplify your data pipelines, and we can also securely share any data inside Snowflake, and you can build data applications on top of Snowflake. And then on the right, we will hook up to any BI tool of your choice like Tableau, Power BI, so your data consumers can run all the analytics and that they need on their data to make data-driven business decisions. So one platform, one copy of data accomplishes all the workloads listed there at the top. Our unique architecture, or special sauce, if you will, is in our multi-cluster shared data architecture, which leverages the underlying foundational technology of the cloud providers to offer basically unlimited compute and storage resources. And you can dedicate compute resources to each workload, so there is no resource contention whatsoever. Our compute layer, also known as virtual warehouse, can scale up and down instantly for performance. It can also scale out automatically as well for concurrency. You only pay for what you use by server second, and the platform takes care of query optimization, transaction controls, collecting statistics, and all those mundane tasks that a DBA would normally do with databases. Snowflake just works with near zero maintenance, and that's why a lot of our customers love about Snowflake. So let's be specific about this. Here is how Snowflake can help. Snowflake helps you to achieve the full potential of your organization's data by making it accessible by all users with governance. Analysts can query data directly over your data lake with unlimited elastic scalability and no resource contention or concurrency issues. We can also help you to run reliable and performant data pipeline that meet your business needs. We can help you streamline your data architecture with less data movement by using Snowflake for data transformations. Processing workloads can run in isolation with right-sized resources for improved performance and pipeline reliability. Each workload can get its own dedicated virtual warehouse and resources with no resource contention among multiple workloads running at the same time, without manually configuring and instantly scale up or down as needed, driving better pipeline performance and lower cost. Snowflake also greatly streamline your data architecture to boost up data engineering efficiency and productivity. Because we are a SQL engine, you have the choice of performance with simplicity, and you don't have to learn a new coding language to work with your data lake. And we are making this even better by adding greater extensibility into your Snowflake pipelines, such as external functions and Java functions. On top of that, we enable a secure and governed data lake, no matter where your data actually is. With fine-grained access control on roles and security like dynamic data masking, your team can work with data in a more secure and governed way. Our data exchange capabilities also allow you to share data easily with governed access and encourage consumption by internal or external users, improving collaboration across the board, no matter where data is. We can be a full data lake, or we can also complement existing data lake. I'm going to walk you through some ways of how Snowflake can complement an existing data lake. Maybe you already have a big investment in data lake. We can make it better. We can supercharge it. So I'm going to show you 4 options The first three are complementary options on how we can help with your existing data lake. The last option is really how Snowflake can be a full data lake. So let's get into those options here, and I'm going to set it up with a basic architecture diagram, and I'm going to overlay the 4 options on top of that. This is the basic architecture of the typical relationship between a lake and warehouse. So this is a complement angle. Data from various data sources flow into data lake in the middle, and then the subset passed on to the data warehouse, and then analytical end users hook up to the data warehouse to do their analytics, and transforms are also done inside a data lake. This is option 1, where we're just acting as a traditional data warehouse. So to be clear, we are not the lake on the left, that is your existing data lake. But as you can see here, that the way it typically works is data flows and it lands in part of the lake as a raw data. And then you're typically going to run some transformations using third-party technology on that data to curate it, transforming it into a manner that can be used by different analytical tools, where it's data science or BI tools. I know some people who are new to transformations saying, hey, Louis, give me some examples. Why am I transforming data in my data lake? So transform is just a process of converting data from one format or structure into another format or structure. And I'll give you a couple of examples. One could be maybe you have data coming into one row table, and then some other data coming into a row table number 2. And you want to merge different columns of those 2 into one table for analytical end users. So that merging function could take data from 2 tables, merge subset into a target table, and your analytics user just query that target table. Or another example may be to do with some aggregation. Maybe you have a lot of files that have individual transactions, but then you want to take those individual transactions and sum them up and put the sum/aggregate onto a target table that your analytical end user will connect to. And then the third one could be maybe you just want to convert a file type from one type to another. That's better for doing queries. For example, it could be maybe you have a CSVs coming in, but you want to convert them to a Parquet because Parquet is built in a manner that's more lends itself towards fast analytics and better compression. But those transformations require compute, and that's what's illustrated here with the cogs. The cogs represent compute resources you need to do transformation. So back to option 1, data length row gets transformed for different analytical users, and then a subset gets sent over to Snowflake, which is there in the blue. But notice we have a copy of the BI data. So already you've got a copies of data, but the data is put into Snowflake, because once it's in Snowflake, then you can really harness our unique architecture for unlimited scale and near infinite concurrency, and it's super performant. So that's just a traditional BI use case. Now, option 2 is for data that's heading into Snowflake, just the transformation inside a Snowflake. Because it's going to make your pipeline more efficient, simpler, more reliable, and it also leverages our elastic architecture under the cover, so we can do things much faster and more cost effectively. So in that case, what's going to happen is the cogs on the top are going to disappear, and this is going to be done inside a Snowflake, and that BI silo inside the data lake is going to vanish, because the data is going directly into Snowflake, and that's what's shown here. So this is option 2. You still have the performant queries, but you now have simpler data pipeline and data engineering effort. Option 3 is you'll notice that there is still a transformation being done in the lower left for data that's destined for artificial intelligence, machine learning type use cases. So you can have Snowflake transform that as well. So we can send raw data into Snowflake. We will use streams and tasks to do any kind of transformation, and then export that back out to Lake for a different tool that might need it in different format. That's option 3. With all these options, I would like to mention that we have a feature called External Table, which I'll demo later, where Snowflake can actually directly connect to data in your data lake to run queries directly on it. And we can also create materialized view over those external tables for an extremely fast performance. I'll get into more details in a second. And then the last one is using Snowflake as the full data lake. So you can send all your structured, semi-structured data and directly in Snowflake. With this option, you have all those benefits I mentioned earlier around extreme performance, no data silos, security and governance, role-based access control, ACID transaction support, and secure data sharing. And because Snowflake leverages the object storage or the blob storage, the cost is extremely cheap. But then you have all those benefits on top, by leveraging Snowflake as a data lake. We have features that can help with these different options. One of them is the external table, as I mentioned, where it lets you directly query data inside of your existing data lake. So inside of Snowflake, you can point us at your raw data and run queries on it. That said, as I mentioned earlier in this talk, it doesn't matter what technology you're using. If you're trying to query against raw data sitting in just cheap storage, it's not going to be highly performant. So what we recommend is with these external tables, we have an option called materialized view over the external table, where data will be ingested up from data lake. So it still remains on the data lake, but a copy is sent up into a table that resides inside of Snowflake. And by doing that, now your queries are going to be extremely performant because it's inside Snowflake, and you can leverage that unique architecture and query optimization that Snowflake offers. We can also leverage Hive Connector. It's an option that's on column 2 there. So you're probably familiar with Apache Hive Metastore. It's popular with not just open source deployments, but even commercial deployments. People use this to manage their tables and files at rest. We can synchronize with that Metastore, so it has all the pointers to all the tables and data in your data lake that you need analytics to. So as tables are changed or data is changed on your data lake, Snowflake's aware of that, and we can stay up to date and totally synchronized with the raw data in your data lake. Streams and tasks enables continuous load and transforms workflows. Streams basically record changes made to a table in a CDC, continuous data capture type format. So it's essentially looking at tables that you select, and it's kind of putting in virtual bookmarks and looking at net new data entering those tables. And at certain points, what you can do then is initiate a task on that stream. The task can execute SQL or stored procedures, which typically is some sort of transformation in nature. Number 4, you have lots of connectors to help you get data into and out of Snowflake. And just the two I'm highlighting here is one, the Apache Spark connector. It enables Spark to read data from and write data to Snowflake. Kafka is popular for streaming, and our connector enables Kafka topics to be streamed into Snowflake in a near real-time manner. And the last one is Snowpipe, which is a serverless Snowflake built utility for continuous ingestion of data. What it does is it automatically and continuously ingests data from cloud storage into Snowflake tables. So as data hits the S3 or Azure Blob Storage, it can ingest in near real time directly into Snowflake tables so that it can help out a lot, especially if you need to analyze fresh current data. Those are just a couple of features that can help with your data lake. Now I'm going to show you a quick demo of Snowflake where I'll be using the external table features to query Parquet files sitting in S3 bucket, and also show you how quickly and easily I can create materialized view of external table to supercharge query performance to complement your data lake. All right, so this is Snowflake Web UI, and I'll be running a couple of SQL commands to show you how I can actually read the Parquet files that's sitting in the S3 bucket. All right, so let's have a look at how Parquet files are organized in the S3 bucket. So as you can see on the trips folder, those files are partitioned based on year. And if you click on the year, it should be by month, and inside a month, they are a snappy compressed Parquet files. And I have about 1 billion record of data in these Parquet files. All right, so let's go back to the Snowflake Web UI and let's run some SQL command. So first, I'm going to create the external staging. So this is basically a pointer to the S3 bucket that I was actually showing you before. And the list command will list all the files sitting inside the external bucket. So in this case, these are the identical files that I show you in my previous tab. All those Parquet files sitting on the S3 bucket. Now I'm going to use a demo schema to create some of these external tables. And if we look at the actual content of those Parquet files, you can see that these are all the semi-structured Parquet files. And as I mentioned before, Snowflake can ingest semi-structured data natively without pre-processing it. So typically, in order for a database to run query on semi-structured data, you would have to pre-process those data files. But in Snowflake, it is a schema on read. So we actually understand the structure, and then using a standard SQL syntax, you can query and join with any data within Snowflake. This is one of the key capability of Snowflake, and why a lot of data engineers actually love working with Snowflake. Next, I'm going to create an external table. So this is basically defining the actual structure of the external table. And as you can see, you can create things like the partition by. So this is so that this external table understands the way the file is actually partitioned on the data lake. I'm going to issue a refresh command to load the metadata for the table, and I have about a 1 billion record of data sitting inside the data lake. So that will basically register the metadata for the table. So that's all done, and let's have a look at the table. So from now on, I can just simply query just like it's a table inside the Snowflake, so inside a database. Okay, there you go. All right. So let's start querying some analytical queries. So in this particular example, I'm actually running some aggregates like count star, average, and you will see that performance isn't like super fast, right? And there's a good reason for that, right? So these we are actually working with the files that's sitting inside data lake. So regardless to any technology that you use, when you run queries over a data file sitting on a chip storage, it's hard to expect a fast performing queries, right? So the great thing about Snowflake is that we are connecting to a Parquet file sitting on the data lake, but we are actually using a standard SQL to interact with that data file. And so, basically you can reuse the knowledge that you have around the SQL. SQL is the most popular query language where you don't have to learn a new coding language or anything like that to work with the data lake. So simply just continue to use your SQL, but still you're working with the data lake files sitting inside the data lake. All right, so it took about 1 minute and 8 seconds to actually query that data. So there was a lot of blob IO that actually happened in the query. Now, if we actually specify a date range, because the data files are partitioned based on year and months, this query should return results much faster because Snowflake understands the actual structure of the folder structure in the data lake. So we really only read files that matches the data range. So there you go, about 20 seconds to do that. These external tables are full-featured tables, so you can use things like CTE, to join with the other data within Snowflake. And again, this is one of the key benefits of running Snowflake on Data Lake, because you're using all the usual functions that you're familiar with the SQL. It's something that you're comfortable with, right? So using a standard SQL command and the syntax, you're actually working with a data file sitting on the data lake. So again, this is one of the key thing about Snowflake, working with a file in the data lake. All right. So we can also make this external table run much faster by creating a materialized view. And the way it works is, the data files is still stored in the data lake. But what we're doing is we're creating a materialized view, but in this case, we're actually aggregating some levels. So we're not bringing in the billion record. Query that materialized view at much faster performance. So now that materialized view has been built, it should be a lot faster. And let's see if we can actually run this query and have a look at the difference. So now the aggregated materialized view is about 7.6 million records versus about 1 billion record on the external table. So the exact same query that we ran previously, let's see how much faster now. So there you go. It is actually a sub-second performance versus what we ran before, which was 22 seconds, which is the exact same query here. So materialized over external table will give you, will supercharge your query performance, and combining some of these features within Snowflake, you will actually have an extremely performant query engine over your data lake. And now that once job's done, you can simply just suspend your virtual warehouse, which means you're not actually paying for any compute. So you have that flexibility of switching on and off at any time, and also scaling up and down, using elasticity of the cloud offering. All right, so let me go back to the presentation and finish that off. So really, just to recap, Snowflake is a true multi-cloud data platform that supports many different data workloads, including data lake. Snowflake can provide robust security and governance to all data, and we are a true data platform as a service offering, meaning all those smarts are provided by the platform where you don't have to worry about managing it. Snowflake is born in the cloud, built for the cloud. So we provide unlimited storage and compute resources, and you only pay for what you use, the way it should be in a modern cloud environment. Learn more at snowflake.com. There's a resources section there, where you can read the latest Snowflake Data Lake related materials. There are links to Snowflake webinars if you want to deep dive into any of the topics around those different types of workloads that Snowflake help to solve. And there are also free instructor-led training, by our virtual hands-on labs. And we provide a free trial for 30 days with $400 credits. So feel free to sign up and then have a go with a Snowflake, and I'm sure you'll love it. So I'll hang around for question and answers and Q&A sessions. So feel free to throw me some tough questions. All right, thank you.
Thanks, Louis, for a great talk and awesome t-shirt, by the way. We have a question on Slack for you from Harmeet. Of the 4 options you've displayed, what is the most common implementation option for Snowflake?
Right, okay, great question. So it really depends on where the customer is at with their data lake journey. But personally, I see quite common patterns around option 2, which is you collect your data in data lake in a raw form, and then you basically push that data into Snowflake, and then you basically do the transformation using elastic compute within Snowflake. So that's a fairly common sort of a pattern that I see. In fact, there are a large, I guess, the streaming media company in US are actually using it for that purpose. So what they call, fast data layer, that's where basically extracting data out from the data lake and then really building that, data for your visualization and analysis purposes. So option 2 is quite common. Option 3, where you do your processing and then you're writing back out to the lake. We're starting to see more and more of that as well, because you can use Snowflake as a sort of a transformation engine and then pushing the data back out into the lake. But where I see a lot of trend is moving is really using option 4, because you can use Snowflake's chip storage, the governance around the data. Because in fact, if you're analyzing data directly in the data lake, you're actually working with files. So you have all sorts of issues around data governance, security, and all that. But Snowflake can address that problem, helping you with securing that data and then applying a proper data governance to your overall data lake. And obviously on top of that, additional workloads that you can actually run within Snowflake. So yeah, so option 2 probably most common, and seeing more and more of option 4 these days.
Wonderful. Thank you, Louis, for that answer. I've got a question here. What is the role of virtual warehouses mentioned in the presentation?
Sure. So virtual warehouse, if you think about database within Snowflake, as I mentioned, we have that complete separation of storage and compute, right? So if you look at database, think of that as more like a traditional hard drive, right? Where your data gets stored. Virtual warehouses are more like CPU within your server. So these virtual warehouses handle processing of all the data loading, the querying of data. And interesting thing is, no data is being stored on the virtual warehouse layer. So you can have infinite number of virtual warehouses all running concurrently on the underlying data stored inside Snowflake without any performance impact. And that's because of that unique architecture of Snowflake of separating storage and compute. So really, virtual warehouses, think of them as just a pure CPU unit.
Wonderful. Thank you for that. And final question, how do you suggest using Snowflake to analyze log files?
Sure. So, one of the common thing about, I guess data lake use cases are storing lots and lots of data, in really cheap storage. So Snowflake can connect to your data lake storage, as in S3 or blob storage, and then really query that data quite efficiently. But one of the great thing about Snowflake is schema on read capability, right? So, a lot of those log files come in a semi-structured format, but Snowflake can handle that type of data without pre-processing it and then loading it into Snowflake. So, the key point here is schema on read and lots of files, leveraging the chip storage, but using Snowflake's capability in optimization, either using external table or using external table with materialized view, or storing directly inside the Snowflake. You would actually get the benefit of having the performance, elasticity, and the scalability using a single data platform, using Snowflake.
Great, thanks, Louis. If you do have any more questions, please do pop them in the chat. As usual, we will be displaying the QR code where you can provide feedback for our amazing speakers.
I'm excited to introduce our next speaker, Mike Goulin. Mike is a software engineer with over 10 years of industry experience, moving around between enterprise and startups, mobile and backend. One pivot later, he landed in data. Currently leading the practice at MX51, building out the platform from scratch and educating the company about what data really means. Here's Mike's presentation.
Hi, my name is Mike Gulin. I'm the data architect at MX51. My talk today is going to be about our data journey, about the journey that we took to get to having a data practice, a data team, if you will. But instead of looking at it from a more chronological point of view, where I just describe everything that we did, I wanted to frame it in a more useful way so that people who are in a similar situation, they can use these learnings for their benefit. And the way that I thought to do it is to view this whole journey and this whole set of problems as one big optimization problem. And I even define it kind of loosely mathematically later on, but feel free to skip that slide if you're allergic to math. But there will be some architecture diagrams which I am told people like in these sorts of talks. So the first part is the background, where I'll tell you more about who we are and what the whole use case was. Then I'll define the optimization problem that I'm talking about. And then finally, I'll apply that optimization problem to a few of the decisions that we had to make along the way, such as storage, BI, and ETL. So first things first, let's look at the overall architecture of what we do. So if you haven't heard of MX51, what we do is we provide services to banks to give them the tools to be able to compete with startups that already do similar things, but where they're the bank. So that might sound confusing, so let's look at an example. You might go to a coffee shop and you'll see one of those things that you see on the left here. They're called point of sale devices or electronic cash registers. So if you order something, they will likely put in all of the items that you want to buy in one of those things, whether it's an iPad or just a desktop with a touchscreen. And then when you say I would like to pay with a card or a phone or a chip in your brain or anything like that, they'll pull out a payment device, which you see in the middle there, which is called payment terminal or a PIN pad, and they will manually enter the amount in there, which is obviously error prone and not a great user experience. So what we provide is libraries for POS vendors to be able to integrate into their software, and a piece of software that goes on the payment terminal to allow the two to talk. Simple as that. So when an amount is ready to be paid for, the POS sends it to the payment terminal. When the payment terminal is all good with the payment, you tapped your card or inserted it and put in the PIN. It reports back to the POS saying all good. What you don't notice when you're using it is that it connects to our backend through this gateway that you can see here. And behind that gateway is all of our microservices. Those microservices handle all of the events that come from the terminal, such as any diagnostics, Wi-Fi, printer is out of paper, things like that. Each of those microservices, as is the usual case, has its own database. In our case, they're all Postgres databases. And we have a few UI components that you see at the top there that connect to those microservices in the form of dashboards, and they display certain things, some of the events. If somebody calls up, one of the merchants calls up and says it's not working, so that the support team can help them with something rather than just saying, try turning it off and on again. And then there's the merchant dashboard, which allows the merchant to log in there and see how they're doing with their transaction volumes and so on. Eventually, though, we started getting some questions internally from product people, marketing people, and so on, that were very analytical in their nature and that required us to look at multiple databases. And obviously, because they're microservices and each microservice owns its own piece of data, you can't just do joins on them. And I mean, another fact about this is that you probably shouldn't be doing analytical stuff on your production databases, but in this case, you can't even if you wanted to. So we decided that it's time to build a data team. And the reason why I say team with the quotation marks is because currently, after just over a year, it's still just me. which, as you can imagine, drives some of the decisions because the resources are constrained. We have to prove things that are useful before asking for more. So when I say Melbourne office on the slide, we used to be a part of this company called Assembly Payments, which is based in Melbourne. We're based in Sydney. And back then when we were the same company, which we no longer are, the Melbourne office started the data journey slightly before us. So it was a little bit of help to be able to compare notes, but because their backend was completely different, we couldn't just copy paste it. I want to briefly mention who I am and what I've kind of done before, just so that you understand where I'm coming from in terms of my thinking. I am definitely not a data scientist. I'm a software engineer. I see things the software engineer kind of way. And I started in MX51 in about 2.5 years ago. And what I started doing initially was actually building out the libraries for the POS software. We have a few that are based on each language. I published the first Java one and did a lot of work on the iOS one. Then I moved on to the microservices that we have that are specifically the terminals talk to. So still kind of keeping within that domain. And eventually now I'm handling the data that includes the data about those terminals, among other things. So it kind of painted a good picture here because I'm not just shoveling data that I don't understand. It gave me a good understanding of what that data is and where it comes from, which is useful. And now we get to the optimization problem that I promised you before. When I entered the data landscape, and I'm sure a lot of people watching this would have a similar kind of situation, similar story, is that you notice there's a lot of buzzwords. Nobody has any pricing on their websites. So you have to talk to sales, you have to spend time kind of defining what your problem is before you can get to it. You can't just say, in most cases, you can't just say, I'll sign up for a trial and, done. And the third thing that I noticed, which is kind of cheeky of some of the vendors that I've seen, where the vendors claim to do a lot of things that they're not particularly good at. So they would have one main functionality that they, got successful for. And then they add these kind of add-ons that technically, yeah, they do those things, but are they the best solution for that problem? Maybe not. So the game here really is make a decision, make it work with other decisions, repeat, rinse, repeat. And to me, that kind of sounds like an optimization problem. So the way that I drew it up was with a high-level architecture diagram where components are specifically what they need to be doing, what they're there for, rather than the implementation. And then we evaluate the possible implementations and choose one based on the metrics that we have. And a metric can be, I'll talk more about this in a second, but a metric can be just the continuous value from 0 to 1 or anything really, or just good, bad, medium kind of thing. Metrics can have weights. So some metric values could be more important to you, some can be less. And finally, you have requirements that basically just guard whether or not you're even looking at something. Because in some cases, if it doesn't pass your initial entry criteria, then you're not even going to compare it. You're just going to say, we can't use this. So that's a requirement. Some of them can actually be more complicated than that because some of those can be both a metric and a requirement, such as cost. Because you may care about, if you can afford something, you may or may not care about how much it's worth, depending on whether or not you can reuse the remainder for other tools. And then you have immutable requirements, which are things that will never change in the foreseeable future, such as, if you're in the financial industry, data sovereignty rules aren't going anywhere. And then you have the mutable ones, where potentially you might have a budget that's too limiting and you can't afford something at the moment, but later on, you might be able to afford it. So if you like some tool for, it does the job wonderfully and you would love to have it, then that becomes, when you relax that requirement of cost, that becomes your desired future state that you want to get to at some point. And this will become clear why we care about this slightly later. The metrics can be up to you. They really depend on what you're trying to achieve. But for me, metrics were business value, no-brainer, top priority, because otherwise, why even bothering? Then you have compatibility with the current state, which is stuff that you already have. Compatibility with the future state, which is where you're going in the future, or you think you want to be going in the future. And then obtainability, how hard it is, how many contracts do you have to sign, how many salespeople do you have to talk to, how much time do you have to, spend on reviewing it in your legal and things like that. And this is the formal definition that feel free to skip. It doesn't really add anything to it. This is just me being nerdy. But the goal here is to maximize the sum of all of your metric values multiplied by all of your weights. That's essentially it. So this expression here, you're saying we want to get the highest possible combination of those things and then the highest possible combination of all of the components. Now we get to applying the theory. And again, this is up to you. You can just say, it's just the vibe of it, if you get the reference. Or you can, painstakingly go through each one, work out what the value is, work out, multiply it by the weight, and then provide that report when you're presenting your decision. This is the architecture that I was working with. Simple as possible. So these are the databases that contain all of the source data. We need something to do the ETL. We need somewhere to store the results of that, and then we need something to visualize it. That's pretty much it. So we look at each one separately. We start with storage because it's kind of the biggest decision, because you don't want to be doing migrations if you move away from things. So option one was quite a popular one, data lakes. And when I say data lakes, I mean you could either do just an S3 bucket with something like Athena to be able to query things on top of it, or you can go all in on something proper like a Delta Lake if you're using Spark. And the compatibility here is pretty good because you just dump everything in that flat storage. So almost everything supports something like JSON or Parquet, all good. Compatibility with the future state, however, and I haven't mentioned this before, because we provide our services to banks, we're kind of slightly dependent on what cloud the bank is using. Currently, we're on AWS, but if the next bank comes along and they're on Azure or they're on Google Cloud, that's where we'll have to be, and that's what we'll have to support. So here you'll see that Athena is easy for obtainability because we already have AWS, but it's bad because if we go to Azure or to Google, we'll have to come up with either a comparable kind of counterpart service there, or we're going to have to find one that's cloud agnostic, such as Databricks with Delta Lake, which would require a separate agreement. Option one was using the kind of cloud vendor specific warehouse offering, such as Redshift for us. The cost part of it was not ideal because if you've used it before, you know that it requires you to define static compute that's always there. So you kind of need to know how much people are going to be using it, which if you're building out a brand new team and if you're in a startup, you don't really know. It might be a hit and everyone might be using it all the time for everything, or it might just be particular people, in finance who need that specific feature there. So it's not really cost effective, at least for our use case. Compatibility is good because it's the same cloud, but again, bad because it's the same cloud. So if we go somewhere else, then we're going to have to do the full migration of all of the tooling to Azure Data Warehouse, I think it's called, and to BigQuery on Google. And then the option that we ended up going with, which is Snowflake. The reason why we went with it is because, first of all, it's affordable and it kind of usage-based, so it grows with you. If you use a lot of heavy compute, you pay a lot of heavy money. If you don't use a lot of compute, then you don't pay a lot of money. The compatibility is pretty good because they're generally pretty well respected in the community. So a lot of things work with them just out of the box, like BI tools, ETL tools. There's always an option to connect to Snowflake. And the main thing here is that it's cloud agnostic because it supports all three major clouds. So regardless of whether we go to Azure or Google, we'll still be able to spin up a Snowflake instance. And obtainability, technically you need a new agreement, but we kind of cheated because our Melbourne office at the time, since they started 6 months earlier, they already went with Snowflake and they already had an agreement that we could kind of piggyback off of. So excellent. That was great decision. I was giving a thumbs up. I think it was off camera before. Now we get to the visualization, which is kind of also important because unless you have a good way of visualizing all of the data that you've collected and transformed, it's useless to non-technical people and even technical people, because what point of collecting it if you can't get insights out of it, right? So option one that we actually did try was QuickSight for the same reason. It's in the same cloud. Here it is. But unfortunately, the compatibility with Snowflake wasn't so great, at least a year ago, because it tends to be more targeting, AWS specific tools such as Redshift, things like that. And you have the same problem of what if we go to Azure? What if we go to Google? Although the obtainability is obviously easy because it's the same cloud. So that was unfortunately out. Tableau, which I hear from a lot of people seems to be the industry standard, because every time you see a dashboard published somewhere, you recognize that it's visualized in Tableau. However, the cost was not great for us because, being quite constrained on resources, I'd love to get hold of it, but it was slightly out of my team's reach. But the compatibility and all of that was good because it's, cloud agnostic, and it supports Snowflake, it supports Salesforce because they're the same company now. Excellent. But there's that issue of signing a separate contract and annual pricing and a lot of money. So that was kind of our, and still is our kind of desired future state. But what we ended up going with is kind of a bit of an open source DIY option called Metabase, which is free, it's open source, you host it yourself. It supports Snowflake, among other things. Because you host it yourself, it's cloud agnostic, so you can put it on Kubernetes, you can put it on whatever you want. And no contracts, you just download it. You have to manage the deployments and things like that, but kind of a small price to pay, honestly, because we're spending, I don't know, like $100 US per month on hosting it. So that's nothing. And with our current demands, it's doing its job pretty well. And then finally the ETL part, which I find to be the hardest decision because there's so many different sources and so many different tools that you have to find a tool that, first of all, you can afford because they're really, really expensive, but also that covers all of the sources that you have now and all of the sources that you're planning to have in the future, which sounds kind of impossible. So option one is just the collective cloud-based, all-in-one solutions, not specifically Fivetran, but Fivetran, Stitch, Illuma, all of those things. The reason why I say Fivetran and Stitch is because our Melbourne office at the time were using them, so they were the kind of specific options that we considered. Downside for us, very expensive, so couldn't fit it in the budget at all. And at least back then, I don't know if it's changed, but the way that they work is they usually usually host it themselves, and you just provide an SSH tunnel into your VPC behind your firewall where you can where they can connect to it and extract all of the data. That's unfortunately really bad because we can't control where it's hosted geographically, which is a requirement for us. So that was unfortunately out even before, the contracts and things. Option two was Matillion, and the reason why I say Matillion separately from all of the others is because unlike the others, you can host it wherever you want. So you can just get it off AWS Marketplace and you can just host it there in your VPC behind your firewall. And this is still, a potential option that we're considering, but at the end of the day, we ended up going with just good old Glue. And I hear you wondering why we went with this, but not all of the other AWS specific things. Well, the reason is, first of all, it's very, very cheap. So even if you go in and then migrate out, you're still saving a bunch of cash. But also, because it's essentially a managed Apache Spark service, what we do is we just write all of the Glue code as just PySpark code, that if we have to move it somewhere, we'll just find another Spark provider, such as Databricks or whatever the Azure and Google ones are. So easy, it kind of all blends in together. And also, one kind of appendix to this is that eventually, when we were happy with Glue and we were starting to think, how do we make it a little bit more kind of mobile and manageable? So we decided to separate out the transformations with dbt, which is the data build tool. So picture I'm trying to paint here is that you're not really locked into that one decision. You can then do an iteration on the iterations and on the iterations, which is what we did here, because the appendix 2 is we also decided to separate out the loading, because Glue was originally just loading things into Snowflake through the Spark connector, because there's no native way of loading into Snowflake, so you have to use the connector. But again, to make it less of a bottleneck and to separate the concern, we started using external Snowflake stages, which is working really well. So what I'm trying to get to here is that although this is our journey and your mileage kind of may vary, what you should be thinking of is that although you can use a framework for decision making for anything, what you really should be using it for is decisions that you have to then justify to the rest of your team, to your management, to your CEO or whoever you need to justify it to. Hopefully this framework, kind of loose framework that I came up with, is useful to you. And if it is, feel free to use it. Consider it open sourced. And that's all I had. If you'd like to hear about anything else or ask me about anything else that's related to this, here are my contacts, and the recording and the slides, if you missed something, will be available on my website that's at the top there. Thank you for your attention.
Thanks, Mike. Really great talk and fascinating to see your decision-making framework there. We've got a couple of questions, both from Slack and YouTube. The first question I wanted to ask was, I'm interested to know what the management overhead is for this approach.
Yeah, that's a good question. Depending on what kind of company you're in, that will be different. So if you're in a more kind of stricter industry, like the finance or health and things like that, where you have to justify things and you have to document every single decision in, I don't know, a tool like Windchill or something like that, then there would be a lot more overhead, because you would have to basically go through and document every single reasoning for every single tool and have committees and things like that. We're in a startup, so for us, it's slightly less overhead. But I guess the whole idea of the approach is that it can be fine-tuned to what your needs are. You can say, if you're in a startup, you can just go with the Vibe sort of approach that I explained in the talk. Or if you need to display the full kind of paper trail, then you can also do that. You can also produce actual measures like I explained. So basically say, these are the metrics, these are the weights, and this is the final score. But also so to talk to your kind of point about updating it, at each point, you're kind of describing the decision in the present tense. So basically, if you're saying that you want to go and try to go with another tool, at each point you're saying that you have your compatibility with the current state, which is the T0, and you have your compatibility with the desired future state if you have one. So anything that's already been implemented and everything that's already been decided on, that's already a part of the current decision. So it basically gets put in the archive, and you're saying, you know, this is the reasoning for that decision. It's in the past now. Now in the future, now we have, you know, this storage, this ETL, this so such and such, and whatever we're building on top of that is based off of that current state. If that answers the question.
Great, thanks, Mike. Excellent talk. We have another question here for you. Why did you not end up going with a data lake?
Yeah, so I kind of didn't explain it so well in the talk because it was one of those decisions that we didn't end up ruling out completely. It's something that we didn't have a specific, you know, final reason to completely discard. And I guess the main reason was just to keep it all to one tool, because the team right now is very small. It's just me. So any kind of management of tools that are separate and in parallel would add the overhead of the resourcing. But one kind of use case that I see in the future for potentially using it would be if we needed for kind of the data science stage of our journey, whenever it would have to be loaded into you know, notebooks and things like that, and it would, if it ends up being easier to load it as a flat file. But so far from our experience of kind of trying it out and building some prototypes, Snowflake has been catering to that perfectly. So again, it's one of those things that we will decide when we get to that decision point where using Snowflake would be the current state, and basically we'll decide it based on the pros and cons at the time.
Great, thank you, Mike, for taking the time to answer them questions for us. If you do have any further questions for Mike, please do pop them in the Slack channel. As usual, we'll be displaying the QR code, so if you do have any feedback, please pop it in there. Next speaker, Jana Sigal. Jana is a data and machine learning engineer with versatile hands-on experience deploying ETLs and machine learning pipelines using technologies like Python and Spark in the cloud environment, and a recent enthusiast of Go. Jana is going to be talking to us today about automating machine learning pipelines with Kubernetes and Airflow. Over to you, Jana.
Hi everybody, my name is Jana Segal, and today I'm going to talk to you about how we used to build machine learning models and how we build them now. Or more specifically, the long tedious manual procedure we had that turned into a simple 3-stage procedure, which is also fully automated, scalable, and highly visible. So after that short introduction, hi, my name is Jana Segal. I am a machine learning engineer at Nielsen, and today I will be talking to you about how we automated our machine learning pipelines using Kubernetes and Airflow. The 3 main points I want to talk to you about is how we utilized Kubernetes benefits and strengths to do this automation. The second point is how we used Airflow to boost this transition. And the third point is some things or some points we wish we knew before we began and could have facilitated our transition to the new automated pipeline. Okay, so a little bit about Nielsen. You might know Nielsen as the rating company in the United States, but Nielsen is actually a data company. And we use that data to build the machine learning models to give our customers insights on their users. For example, we will use a machine learning model to build segments on users. For example, people who like to buy shoes or people who love dogs. And our customers can utilize those segments to boost the performance of their marketing campaigns. Okay, so a little bit about the team. I'm located in the Tel Aviv branch of the company, and the team lead and the solution architect is Arun, and he is located in the NYC branch. We are usually working with typical machine learning tools like Scala, Spark, and Python, but recently we have started to use Kubernetes and Go, as we will see in the next slides. Okay, so how did we use to build models? In the first stage, the user, usually a data scientist, will write a configuration file for all the models he wants to build. These models are called group models because they have some similar features. These configuration files will typically look something like that. Here's the group name, which is consistent through all the rows. The model name, we have here 3 different models, and each model has its own steps that we want to run in the machine learning pipeline to create the model. In this case, models 1 and 3, we only want to run the pre-processing step. But for model 2, we want to run all the steps: the pre-processing, the model fitting, the model evaluation, which includes the confusion metrics, and the reporting stage that collects all the data that was created during model training, and we want it to be sent to the user. So in the next stage, the user launches a Dockerized application we call Message Producer that reads this configuration file and populates a queue, in our case a RabbitMQ, with 1 message per model. And this looks something like that. We have here the group ID, the model name, and most importantly, the machine learning pipeline steps we want to run on this model. In this case, all 4 steps. In the next stage, the user will launch multiple containerized applications we call message consumers. Each application will read 1 message from the queue and run all the steps indicated in the queue for that model. So each message consumer reads from the queue, builds the model, reads another message, and so forth until the queue is empty. So what are the problems with this pipeline? First of all, it requires the users, the data science people, to use tools that are not related to their core business. They should be handling the model improvement and data science related things and not the DevOps related things of this process and repetitive steps. Second problem is the solution is not scalable. Since each user decides how many consumer instances to launch, this is not efficient, and also the user might forget to turn off these machines, and this is simply not efficient. And the third point here is that we don't have visibility, whether it's common errors or how many resources each model requires from the machine. So these are problems we need to solve. So the solution or the new architecture includes Kubernetes and Airflow joint effort. But before I'll show you our new solution, I would like us to get to the same baseline as regards to what Kubernetes and Airflow are. So Kubernetes is a platform that allows you to manage your containerized workflows. Its main, or one of its important features, is its high scalability. It allows you to scale up and down with ease and have many replicas of the same containerized application and so forth. And another important point I want to stress out is that it has a very popular command line tool called kubectl that allows you to view and monitor and deploy objects inside the cluster. And I will mention it here because we will be using it down the road. So how does a basic unit in the cluster look? This is a node. This is a basic unit of the cluster. A node is simply a compute engine or an EC2 instance if you're working with AWS. And inside you have logical units called pods, and each pod can have its own containerized applications. For example, message consumers we saw in our old solution. Also, each pod has its own internal IP address, and we can reflect that to users outside of the node if necessary. So that's what I had to say about Kubernetes. Now, Airflow. Airflow is a simple platform to manage your workflows, and it is built of a simple component called an operator that represents a single task and is implemented in Python. Let's take a look at an example to have a more clear vision. So this is a simple Airflow DAG. Our DAG is called Hello World, and a DAG is a direct acyclic graph, or simply put, a pipeline with steps. And here we have two operators, a dummy operator and a Python operator that prints hello world, and the connection between them. First dummy operator, second hello world operator. And this is how it looks in the UI. Quite simple. Okay, now we're ready to look at the new solution. So in the new solution, the data scientists write configuration files and drop them into an S3 bucket. And this is where their job ends. Now they only wait for a message to be sent to them that the model is built. So we have a bucket with multiple configuration files, which is pulled by an Airflow DAG in a predefined schedule. Once the Airflow DAG finds at least one configuration file, it takes them and populates one queue per group model, meaning each group model will be processed by a different queue and a different workload. The next step, the Airflow DAG launches objects called jobs inside the cluster. Here you can see this job number 1, which is responsible for queue number 1. So all the message consumer pods that will be working on this job will be reading messages from queue number 1. So each message consumer will read a message and then deploy another pod, which is the worker pod, and this is the component that will be actually executed the machine learning pipeline. Once the building of this model is done, the message consumer pod will read another message and so forth. Okay, so how does this solution solve our issues? First, let's talk about automation. How do we actually deploy jobs to the cluster? So the simplest way to do so is by writing a configuration file and deploying that configuration file to the cluster using the kubectl command we have discussed before. So let's look at a few interesting features inside this configuration file. First, the parallelism. Here we indicate how many pod instances should work on the job, in our case 3. Second point is what is the image that the pod should run. In our case, it's a message consumer image. So each one of these 3 pods will be a message consumer, and we'll be taking that image from our Docker repo. The third interesting point is that we can pass an environmental variable with the queue name to the pod, or any other environmental variable for that matter. And that's how the pod knows from which queue to read. Last stage, we can just use kubectl apply on the configuration file and the job will be deployed on the cluster. Okay, so let's look at the pod configuration file and some interesting things here. So first of all, we can create our own custom label that indicates for each worker pod, a pod that executes the pipeline itself, it will indicate to him which consumer pod launched you. And this will be very helpful when debugging or tracking error messages. The next stage, we want this pod, the worker pod, to launch all the step containers of our pipeline, pre-processing, feed, etc., and we indicate the message here. Unfortunately, this solution does not work. Why? Because pod containers are executed parallelly, meaning pre-processing and feed in this case will run at the same time, and this is counterproductive, obviously, because in machine learning pipelines, you will need the output of pre-processing for the feed stage. So we need to solve this. And along comes a parameter called init containers. Init containers is a parameter needed in the pod to prepare the environment before running the real container. and init containers are run sequentially. Therefore, we just move our containers to be init containers. And that's how we bypass this problem. Now, pre-processing, fit, eval, and so forth will run one by one, and the real container will be a dummy container that simply prints "I am done" or "Hello world." Another issue we have with this flow is that all the steps currently are hard-coded in the configuration file. But we want each pod to run only the steps indicated in the message. Therefore, what we did is we used Jinja templating. We took a template of this pod configuration file, and we added a for loop. So before deploying this pod to the cluster, we will render this template with the steps parameter, which will give us the key and value of the images we need to run inside the pod. So each pod will run a dynamic amount of steps, and this will give us flexibility and solve our issue. Okay, that's all about automation. Now let's talk about scalability. The easiest way to do so is by example. So in this example, we have a pod we want to deploy inside the cluster. This is our cluster. And for now, nothing happens. Nothing happens because we don't have any compute instances or EC2 instances on the cluster. So once a pod is deployed on the cluster, we can run the kubectl command and see that the pod is pending, because in the meantime, a node is being spun up. Once the node is ready, the pod will be launched on the node and start running. Nice. Now, what happens if we have another pod that we want to run? If that pod fits the node requirements and the resources that the node can offer, then the pod will be allocated on the same node and start running. If not, a new node will be spun up, and the pod will be in pending mode until that node is ready. And once it's ready, the pod will start running on it. Now, how about scale down? Well, as soon as one node's CPU utilization drops under a certain threshold, the cluster knows that the computing on that node is done and will scale it down. And that's how we will reach the empty cluster form we can see here. So this is very resource tight and very efficient, as you can assume. Okay, now let's talk about scalability from the point of view of Airflow. So if you recall, our pipeline was built out of dropping configuration file into a bucket, Airflow triggering, population of queues, and launching one job per queue. Let's translate it to Airflow. It looks something like this. We can see the parallel operators with the steps of the scheme in the first bullet. So here is operator that checks S3 files. Here is an operator that populates the queue by producing messages. And similarly, here is the operators that launch jobs. We have one operator per one job, and each job represents a configuration file. And this is dynamic because each time Airflow polls the bucket, there's a different amount of configuration files there. Unfortunately, this does not work. Why? Because Airflow workflows should be static, or at least slowly changing, like, for example, database schemas. So we can't launch a dynamic amount of job launching operators. What should we do? Well, we know that in Airflow, we can create our own custom operators by extending the base operator and implementing the execute class. Also, fortunately, when we were working on this solution, another team in the company already had their own job launching operator in Airflow. So what we had to do is simply extend this operator to launch multiple jobs in a loop instead of one. Let's see how something like that should look. This is a simplification of our Kubernetes multi-job operator. We have here the task ID, the name of the task, the list of jobs we want to run, job 1, job 2, A job template, this is a template of the YAML file we saw before, and we will populate its features per job. A connection ID, which represents the permissions this Airflow instance has to launch jobs inside Kubernetes, because they need some sort of like handshake and authorizations between them. And the DAG, the direct acyclic graph, this operator belongs to. So now the new solution looks something like this. Instead of multiple launch jobs operators, we only have one. And inside of it, we launch the jobs in a loop. And we are not afraid of the time it takes to launch those jobs in the loop, even if we have 100 or 1000 configuration files, because the action of launching a job in the cluster is very simple. Most of the computation happens afterwards when message producers are, message consumers are launched. So that's good. Okay, lastly, let's talk about how we gained visibility. First, usage visibility. Machine learning pipelines and machine learning steps usually require a lot of CPU and memory resources, and we want to see how much exactly. So what we did is we installed a tool or a platform called Prometheus on the cluster that collects monitoring metrics on all the objects that we are interested in, like nodes, pods, init containers, etc. Next, we paired it with a dashboarding tool called Grafana that collects those metrics and exposes them on a very simple UX-oriented dashboard. This is a very simple architecture of the solution. Here are the various objects on our cluster. Prometheus that also sit on the cluster collects those metrics and sends those to Grafana, and Grafana shows us various dashboards we want to see. Let's look at an example. Okay, here we can see the CPU and memory utilizations of two init containers or two machine learning steps, pre-processing and fit. We can use this in various ways. Let me indicate two. First of all, we can see if our containers behave unexpectedly. For example, if the fit container accumulates memory more and more and more and does not release unneeded memory. So we can debug our resources. And secondly, we can tighten the requested resources by each container, because we see, for example, that pre-processing step only requires 19 giga of memory. So we can ask less than 120 or something like that. So this is a function that Kubernetes allows us to easily install and use on the cluster. Second visibility aspect is error monitoring. To do error monitoring, we use something called ELK stack. There are basically three simple steps for that. First, we install a component called Filebeat that collects data, collects ORAL logs, and sends them to Elasticsearch. Elasticsearch indexes this data and stores it. From then, Kibana, the visualization tool, extracts this data and allows us to query it and aggregate it. Let's take a look at the common dashboard we customize. So this is our customized dashboard. We added a column for the pod name because this is a column that is very easy to query on. Also, we added a column with the job name that launched this pod, that is responsible for this pod. So for example, if there's a problem with the job, it will affect all pods and we will be able to see that. And lastly, we have the error message itself. What we can also see here is it is quite easy for people that are not necessarily from R&D to query and debug the issues without having to do any coding or dig deep into the cluster. So this is a very comfortable way to gain visualization on the cluster. In the last slide, I would like to talk to you about all the things we wish we knew before we started and could have made our lives a bit easier. So first of all, Kubernetes is great, but it's also great specifically for machine learning, primarily because machine learning computation requires a lot of resources and in different volumes. So scalability plays a very important part here. Secondly, visualization of our process, of our machine learning processes, allows us to optimize them and fix various bugs like utilization or common errors. And this is very important, especially when a lot of resources and cost are involved. And this brings me to the third point, the cost efficiency of the solution. Even just from the point of view of having data science be focused on their core business and not do DevOps solutions. And another important point that we learned is that even though our initial solution wasn't efficient, it was divided into small containerized units. And this made our transition to Kubernetes much, much easier. Therefore, the point here is that if you plan to move on to Kubernetes in the future, you should start building your code appropriately and prepare for that by containerizing your application into small components. Another point, which is more specific, is that we learned that Airflow pipelines should not be dynamic. They should be static or slowly changing, but that's okay because Airflow has other benefits, like you can create your own operators, and with those benefits you can bypass the issues that are created with the this by design feature. And lastly, we learned that Kubernetes pod containers run in a parallel manner, but that's okay because we first of all can bypass that with init containers. But currently, there are also other popular solutions like Argo and Kubeflow. And once we have a working solution with the init containers, we can, in future releases, migrate to more sophisticated solutions. Okay. So I hope you enjoyed the talk or at least learned something new. If you have any questions, please feel free to contact us and have a lovely day. Thank you.
Thank you, Jana, for that fantastic presentation. That was quite fascinating. I'm interested to know, one of the questions that we have is how does Airflow connect to Kubernetes, please?
Yeah, so actually in the multi-job Kubernetes operator we implemented when we extended the base operator, we had a parameter called connection ID, where we pass a variable from the Airflow environment that contains all of our kube config, the part that has all the credentials and various certificates and so forth to connect to Kubernetes. And we pass it to the operator, and inside we load it as a temporary file and serve it to the Kubernetes API, so he knows that like this Airflow instance knows who you are, and he can deploy the jobs into yourself.
Awesome, thanks, Jana. We have another question here for you. What are your guiding principles for what you should and should not do in Airflow?
Yeah, so also based on the talk, I think maybe the important guideline here is that Airflow is a good tool for data engineering and so forth. So you can, even if you have these features that are not wanted, like you can't create a dynamic part inside of a DAG, Airflow will have substitutes to mitigate this issue. Like, for example, the solution we suggested of creating a new operator, or even creating sub-DAGs and so forth. I think that's about it.
So thank you for that, Jana. Really appreciated that. If you do have any further questions, please pop them in the Slack for Jana. As usual, we will be displaying a QR code where you can provide feedback to our amazing speakers.
For those just checking in, my name is Leo. I'm currently working as a data engineer at the cloud consultancy iTalk and passionate about all things data. I'm here today with my co-host, Amit.
Hello, everyone. I'm a data and machine learning engineer at ThoughtWorks Australia. I have a special interest in streamlining core engineering practices in the world of data, and as well as designing machine learning architecture that makes productionizing ML easy and scalable.
Thanks, Amit. Let's move on to our first speaker that I'm delighted to announce will be Marta. Marta is a developer advocate at Ververica and a contributor to Apache Flink.
Today, Marta will be talking about change data capture with Flink SQL and Debezium. And we'll also demo how to use Flink SQL to easily process database change log, data generated with Debezium. So let's welcome Marta.
Hi, everyone. Thanks for taking the time to attend this talk. I'm Marta. I'm a developer advocate at Ververica, and today I want to talk a little bit about change data capture and some of the tools that make it easier to put it into practice effectively. So for those of you who have never heard about Ververica, you might know it as the company of the folks who created Apache Flink. And this means that I'm really fortunate to work every day with the core Flink maintainers and to be involved in this really thriving and active open source community. And what Ververica does besides working on Flink is provide an enterprise Flink distribution called Ververica Platform that simplifies a lot of the operational side of deploying and maintaining streaming applications in production. And since the beginning of last year, we are part of the Alibaba Group, which you may or may not know is also one of the biggest users and contributors to open source Flink out there. So before turning to Flink, I was working as a data warehouse engineer for a couple of years. And this is a pretty good depiction of me at work. So if you were ever involved in building data integration pipelines for analytics, in a company that is not necessarily running on the latest cutting edge tech, you probably know that there's nothing very sexy about being a data warehouse engineer. There is a lot of legacy, a lot of technical debt. You have a lot of late data or just this we'll fix it later data. And you really have no option, but with time, just learn to live with it, which is not very good. So this is all I knew for a long time. So you would have this monolithic application that was backed by some transactional databases. You would write these huge heavyweight ETL jobs to integrate the data, enrich it, and so on to make some sense out of it. And you would give your stakeholders something that serves a specific business purpose. So in this universe, databases are still very much seen as these static sources of data records, like just a collection of state about your business that is sitting there waiting to be queried. And for a long time, I was also guilty of thinking about databases like that. But in reality, most of the data that is stored in these databases is continuously produced and is constantly evolving and changing. And it's the logic that you use to query this data that doesn't change very frequently. And when you start looking at things from this perspective, you seriously start questioning a lot of things. Like, if our data is being continuously produced, then why are we giving stakeholders data from yesterday? Why are we not offloading the load on the database throughout the day so that people don't have to wake up in the middle of the night because some query ran out of memory? And in general, why are we just letting all this data go stale before we process it? And let's be honest, no one working with data integration wakes up thinking, well, I really can't wait to scan a production database for changes using a 100-line query with 1,000 business logic conditions. That will probably fail at some point. So what I described so far is actually also change data capture. So this is not a new concept in itself. the idea behind it is pretty simple and is not that recent. So what you want to do with change data capture is you want to track and propagate data changes in a database to downstream consumers. And so whenever you get insert, an update, or a delete operation in your database, you want to capture this change in state and make it available to, in our case, our analytics workloads. So when change data capture is done right, it can be a huge enabler for different use cases, not only in the analytics space, but also for things like caching validation or syncing between microservices and so on. And if you want to learn more about change data capture and the use cases and patterns that it enables, I really recommend that you follow Gunnar Morling and explore his collection of talks. He's the main Debezium guy, and he has really, really good insights about this topic. So there are basically two different ways that it can go about change data capture. The first one is what I talked about so far and what I was using on a daily basis at work before, which is called query-based change data capture. And what happens here is you periodically poll your database for changes, and each time you just ask, did anything change since the last time I checked? And this has some advantages for some use cases and is a bit simpler if you, for instance, just want to track a slowly changing dimension or something like that. But for most use cases where what you want to do is react to data as soon as possible after it's generated, it kind of carries a lot of problems. So the first problem is that some data changes might get lost in between the polling of the database. So if you're running this query every 5 minutes and in this interval a record changes state twice, you can't really capture that. And in the same way, if a record is deleted, you just really lose track of it. There is no way for you to know that the record is no longer there. And there's always a trade-off between how frequently you can query your database and also the load that you're incurring on it. And this is especially true if you're sharing resources with other teams. So there must be a way to do this differently, right? And what if we just tapped into the transaction log? So all databases have an immutable log that just registers all the transactions that are successfully executed in the system. So in Postgres, this is called the write-ahead log. In MySQL, it's the bean log. And this is what a database administrator would use for disaster recovery to kind of roll back the state of the database to before everything went to shambles. And this is the base of log-based CDC. So what you do with log-based CDC is you use this transaction log, you just tail it, and you get the latest changes, and you propagate those downstream in near real time. So this guarantees that all data changes are captured because you're reading from the log, and it just registers all operations, including deletes. And you get more context on the actual changes, so you can get the state of a record before it changed. After it changed, you can get the operation that was performed on this record and other very useful metadata to kind of reason about your data. And also because you are no longer reading from the database, you are reading from this transaction log. So this has very minimal impact on your source databases. So your DBA will probably love you for this. And the most popular tool to do this log-based CDC these days is Debezium. And what's great about it is that it gives you a standard format for this change event. So you can process the data in the same way, regardless of where it's coming from. And what it does, in essence, is really transform your databases into event streams that can be consumed in near real time. So Debezium is built on top of Kafka and provides Kafka Connect connectors for the most common databases, so MySQL, Postgres, MongoDB, and so on. And once the change events are pushed to Kafka, you can basically consume them with pretty much anything, including Flink. If it's your first time hearing about Flink, in the simplest form, what it does is it continuously consumes data from this disparate amount of sources, like the change streams from Kafka that I was just talking about. It applies some stateful computations on these data streams and builds up some context about the data that it's processing as it goes. And then it just produces some kind of output. So it can be an API call, updates to a database, other data streams, and so on. So what makes Flink really powerful and different than other stream processors out there is that the way it handles this context, or the way it does state management, which gives you some really, really good properties, like enabling you to process streams with low latency and also high correctness guarantees. And what makes Flink really flexible is that it does one at a time event processing, or what some people still call these days real streaming. And this gives you a really great primer to address a wide range of use cases, from streaming analytics and machine learning to these Lambda-style event-driven applications. And as a user, Flink gives you different APIs to choose from that trade off how easy they are to use and how expressive you can get. So at the higher level, you have APIs like SQL, Table API, and PyFlink that are a bit closer to this relational way of thinking about data. And these APIs allow you to express your problems in a very concise way and kind of offload all the operational heavy lifting to Flink. So you don't really have to think about state management or any of that. And as you progress down, using the APIs gets a bit more complex, but you get more and more control over the programs that you're building and how they are executed. And when you reach the core building blocks of Flink, there is really no limit to what you can do. And for some use cases, you need Flink's full work horsepower. You need to perform really complex computations, and maybe you need to customize a lot of your programs. But for a lot of others, you don't. And CDC is a great example of a use case that can benefit from how simple it is to use Flink SQL. So the nice thing about providing a SQL-based API to the streaming is that everyone knows SQL, right? If you've used a database before, you recognize this as standard or ANSI SQL. And this means that you also know how to use Flink SQL from the get-go. And you'll notice the resemblance in a bit when I start the demo. So what's different about running SQL on top of a streaming engine? So unlike what happens in your regular database where you run your query and the engine takes a snapshot of the table at the time the query was run, and then it just computes the results based on that static snapshot. What happens in a streaming SQL engine is that your query is continuous and never ending. So you first deploy your query, and then whenever there are some changes to your tables, these changes are just continuously consumed, and the results are continuously updated. So, like I said, this is long-running, the queries are long-running, and it only really finishes when you actually stop the job. In a nutshell, what Flink SQL gives you is this high-level, relational-like way to query data streams using this language that you already know. So it's optimized to handle batch and streaming workloads in a unified way. So this means that you can use the exact same query to process real-time data and, say, a file stored in a S3 bucket. And besides all the operations that you're already familiar with, like joins, aggregations, filters, it also has support for advanced operations like time traveling, pattern matching, and things like this. And with something as simple as SQL, it really allows you to build applications that leverage all the benefits regarding performance, scalability, and consistency of any other Flink program written in Java or Scala. And you have a whole ecosystem around it that makes it really easy to write end-to-end streaming applications using just SQL. So now we can get down to what actually brought us here in the first place, which is Flink SQL and change data capture. So since Flink 1.11, which was released last month, Flink supports to consume JSON-encoded Debezium changelog from Kafka. So the way to do it is simply to use the Debezium JSON, the Debezium JSON format in the properties of your Kafka back tables, and then Flink is able to just deserialize the format. And now to a quick demo about how you can easily just set up a CDC pipeline using Flink and Debezium. What are we doing with this demo? So for the sake of this demo, we're looking into some fake insurance claim data related to animal attacks in Australia. And what we'll try to do is basically get a change data capture pipeline going, simplify some things by using Flink's integration with catalogs, and then maintain a materialized view in Elasticsearch that is updated in real time with whatever transactions are happening in Postgres. The demo is using a Docker Compose setup that you can clone from GitHub. I dropped the link down there. And the setup spins up a couple of containers that run different services. So we have Postgres that is bootstrapped with some demo data, which will be our source of change events. We have Kafka and Kafka Connect to deploy Debezium to get these change events. And we have a Flink cluster and a SQL client that will allow us to submit some queries to Flink. And finally, we are syncing the whole thing to Elasticsearch and Kibana. To spare you some time, looking at my terminal, I started all my services before. So the first thing we can do is check that everything is up and running. So we just use Docker Compose PS, and we can see that all the services that I mentioned before are up and running, so we can get cracking. So the first thing we can do is check that we have some data on Postgres. So we can start our Postgres client here, and we can just check what tables are in there after the client is up. Okay, cool. So now we can just check in the information schema what tables we have in this database. So we have 2 tables, members and accident claims. And now we can just do something like count how many records we already have from the bootstrap that we did. So we have 1,000 records in this table. That's cool. And what we need to do next is deploy our Debezium connector. So for that, we will post a JSON document with the configuration of the connector to the Kafka Connect running service. And this should give us back the properties of the connector. Cool, so you can see here that we are using the Postgres, the Debezium Postgres connector. We want to track our database, which is named Postgres. We are using PG claims as like the prefix for any Kafka topics that are created from this. Yeah, then there's some properties that are set. I will explain it a bit better in the README of the repo, just to make things a bit easier, like decimal handling mode and that kind of stuff. So what Debezium does, unless you tell it not to, the first time it connects to a Postgres server, is that it takes a consistent snapshot of all the schemas. So what should have happened now that we deploy the connector is that we already see events in our Kafka topic. So we can just use the Kafka console consumer to have a look in there. This might take a little while. My computer is literally on fire from Docker. But so we saw that we had a count of 1,000 events. So that's 1,000 records in our Postgres table. So this is kind of what we should see here. Here we go. So you see that it's just reading the topic that we created from our Postgres table using Debezium. And you can see here that we have kind of like the tail of our topic. So what happens is that you see in the payload, you see the before, Because this just comes from the inserts that we did when we spin up the container. There was no before state, it's an insert. And then you get the whole description of this record. So this is good. And what we can do next is actually do some changes on Postgres, and then we should be able to see these operations being captured in Kafka. So let's do first an insert of a new record, and we will follow that with an update of that same record. So just update to get like a receipt in there. And then we can immediately also delete the record. So what we should see when we go back to Kafka, we should see 3 events. We should see insert, we should see update, and we should see the delete. So let's have a look. We have here the insert. You can see here that we created a new record, and then it was followed by an update, and this is the state before we made the change, and then you also get the state after, which should have like the new receipt that we added. And then also you can see here the delete. And we can move over now to see how we can make this, how we can now propagate this to Flink. So we can start the Flink SQL client. When you see a squirrel, it's a good sign. Okay, so now we have our Flink SQL client. This is basically a tool that you can use to submit queries or jobs to Flink. What we want to start with is create a catalog that will give us access to the metadata of the external tables that are stored in Postgres. So we run that, so JDBC catalog. Cool, and we can use the catalog to check that we have the same tables that are available on. The thing we want to do is create a table to consume the change events from. So it should have the same schema and constraints as the source table. And like I said, with the catalog available, we can just easily do this. So you see, we're using the Kafka connector. We are tapping into our PG claims, accident claims topic, and we are using the Debezium JSON format. Also, we are scanning from the earliest offset so that we can get what's already, so we can consume the topic from the beginning. So we do that. And since we're already here, we can also create a JDBC source table for the existing members table. So like this. And after we created all our tables, we can just change to the default catalog. You can see that the tables that we created are here. And now we can select from our changelog table. So here we go. We should hit 1001, which is all the records that we have in our topic. Oh, actually just 1000 because we deleted the record. So what we can do now is just do the same that we did to test how the integration was going in Kafka. So now we can just insert a new record, and you see that it is immediately propagated to Flink. And same thing if we do an update on this record, you can see that the claim total received has changed. Now we can also just scratch it, and the record should be deleted from the Flink table. Cool. So now imagine that we want to calculate and visualize the aggregated insurance costs per insurance company. And we want to bucket this by the accident detail, or what animals are causing the most harm in terms of costs. So we can create a table that will sync to Elasticsearch like this. And by specifying a primary key, we are telling the Elasticsearch sync table that we expect it to work in absurd mode so that we can update our aggregated values whenever there's an event that changes in them. And also we are using an index that I haven't previously created on Elasticsearch, but Flink will take care of creating this for you. So we can just create this table, and now we will just insert with a query that basically creates a concatenated or creates a key that is concatenated from the insurance company first for characters, and then also part of the accident detail field. And then we are aggregating, or we are summing the total of claims per insurance company and accident detail for every claim that doesn't have a status that is denied. So if we run that, it's submitting a job to the cluster. So now we can switch over to Kibana and create a simple dashboard that then we can use to see the changes in real time. I will skip over this part and come back when we have a dashboard up. But you can see that we already have here the aggregated insurance costs index that we created by creating a sync table with Flink. You can see now that we have created a dashboard in Kibana that is basically showing the aggregated costs per insurance company, and then also the aggregated costs per accident detail, which is basically the animal that caused the accident. And now what we want to do is we have a small data gen script, and we will run that, and hopefully what we can see is this dashboard updating in real time. So we start this, we move back to Kibana, and we should see that our values are changing. So basically what the DataGen script is doing is just inserting every half second new records. And you can see when Kibana updates and refreshes, you can see the values just change. That's about it for our demo. So I would like just to wrap this up by telling you that Flink SQL is used at massive scale in companies like Alibaba, Uber, Yelp, and Lyft. As an example, if you take Singles Day in 2019, which is probably the biggest shopping festival in the world, Alibaba was running, I think, around 10,000 Flink SQL applications on over 5,000 nodes, and dealing with a data size of around 985 petabytes. And at peak, they had a throughput of 2.5 billion events per second, and they were still able to process that with sub-second latency. And their biggest job was handling 100 terabytes of state. So this should give you a good idea of how far you can push Flink. And yeah, Flink SQL is standard. So if you know SQL, you will know how to use Flink SQL. It provides unified APIs that allow you to work the same way with batch and streaming data, and it has a really growing ecosystem of integrations around it. So I would just like to add that in the upcoming releases regarding CDC in particular, you can follow what's planned in this umbrella ticket, but the most relevant features that are coming up is support for Avro. So this will be much better to work with actually the schema information that Debezium can also provide you. you will be able to do temporal joins with changelog sources. And at some point, batch support will also come to CDC. I recommend that you check this open source Flink CDC connectors that were developed by one of the main engineers that is working on CDC in Flink. And these are using embedded Debezium, so you don't really need to deploy Kafka Connect and Debezium itself, so you can check it out and give it a try. And lastly, I would just like to really thank DataEng Bytes, especially Peter, who's been like a really great supporter of Flink and of bringing Flink down under. So thank you so much, and it was a pleasure to do this talk for you.
Thanks, Marta. Impressive demonstration. What a great way to implement CDC. It's awesome to see such a powerful solution implemented through Flink SQL.
Yeah, that was fantastic. It's amazing to see the scale you can take Flink to. Let's move on to some of the Q&A. So we don't have an awful lot of time, but we'll answer one of the questions from Francisco. It was, why would we use Flink SQL compared to other tools such as Kafka Streams or SQL?
Yeah, so real quick, I think this is probably one of the things that always pops into people's mind first when they hear about Flink or Flink SQL, and it's always a very political question. But I think the answer really is that it depends a lot on your use case, the stack you're already using, and your requirements. And if you're already using the whole Kafka stack and you're already used to K-streams, KSQL is very convenient and can be very powerful. What I think is really great about Flink and Flink SQL is really like I said just a minute ago, like the scale you can take it up to with such a simple language. Like you can really harness the full power of Flink and everything that's amazing about Flink by using Flink SQL, basically. And when you move beyond trivial use cases and you really need to scale and go all out, and you really need to do this with like really strong guarantees. And when you start to deal with things like huge states, something like you have Windows spending days or something like that, you really start needing a lot of these nice things that Flink offers, like this fault tolerance mechanism, and in general, just how it handles state. So I think that's basically the idea, but it always depends on your requirements and what you're going for.
Yeah, awesome. Yeah, once again, right tool for the job. We'll now put a QR code up, and if you'd like to rate Marta's talk, please scan it. Your feedback's always valuable. Also, Marta will be available on Slack for any further questions.
Now we are going to have Robin. Robin is a senior developer advocate at Confluent, the company founded by original creators of Apache Kafka, as well as Oracle ACE director. He has been speaking at conferences since 2009, including KubeCon, JEVOX, Strata, Kafka Summit.
Today, Robin is going to show us an exciting talk on how we can build a Telegram bot with Apache Kafka and KSQLDB. In this talk, Robin will show us how we could ingest, filter, enrich, aggregate, and query data with just Kafka without needing any other data store. Without further ado, let's welcome Robin.
Good morning, good evening, good afternoon, wherever you're joining from, welcome to this talk. My name's Robin Moffat, and I'm coming to you today from the lovely northern English town of Ilkley. And you can see in the photo here, there's lots of lovely moorlands nearby. It's a very nice place. And from here, we've got lots of towns and cities nearby that we can go to. And when we go to them, we sometimes drive there. And drive there, we need somewhere to leave the car. And so we've got car parks nearby. In the west of Yorkshire, we say car park. Elsewhere in the world, they probably say car park. Anyway, car parks, you need somewhere to park your car. And sometimes there's space available and sometimes there isn't. Which leads to questions like, well, which spaces are there available? And which car park has got spaces? And is there one that's nearby where I actually am? And actually, can you tell me when there is a car park that has got some spaces? Because sometimes they get busy. And even, it'd be quite interesting to know how it fluctuates over time. So maybe we can plan our journey around when there are empty spaces, which is maybe overanalyzing it, but what's this kind of thing if we can't have fun? So as I say, my name's Robin Moffat. I work at a company called Confluent. Confluent are one of the companies behind the open source Apache Kafka project. We've got our own distribution of Kafka called Confluent Platform, and also a managed Kafka and Confluent platform in the cloud called Confluent Cloud. I've been doing this kind of thing in data and analytics for a few years now. I like blogging an awful lot. I do conference talks and meetups. I've even got my own YouTube channel, courtesy of Lockdown. So what I want to show you today is how we can build something using a simple REST API like the one that the car park happens to expose, telling us how many empty spaces are out there at the moment, and how we can build something around that using a few different tools in the toolbox. We can use something called Telegram as our platform for the interface out to the user. Telegram, if you're not familiar with it, it's kind of like WhatsApp or Facebook Messenger. It's a generic messaging platform that's got all the extra bells and whistles that they always add on, but at its heart, it's a messaging platform. It's got an API, so we can write a bot that goes against it and sends the messages and can interact with us. So that's the end of the slides, because it's much more interesting to actually see this kind of thing in action than it is just to see a bunch of slideware. I'll share the slides afterwards, and the slides have got all the kind of like diagrams and the kind of stuff that you'd expect, but let's actually go hands-on now and see what it looks like. So to start with, let's have a look at the bot itself. So Telegram API, it's very nice to work with. And I've got this simple example here that I'm going to show you. I'm using Go, partly because it's been a project of mine to learn it recently, and partly because that's the example I have to hand. And so in this example here, this is just for the Telegram bot itself. We're not doing anything car parky yet, we're just looking at the Telegram bot. So here we're using the bringing in the library itself. This is a third-party one that I've brought in, very nice and easy to work with. We need to pass in a token, which you go and create a bot in Telegram and you get an API code. And from that, we connect to Telegram, we subscribe to updates, so when someone sends us a message, tell us about it. And from there, we just set up a loop which says, well, we're going to sit and wait using this for loop here on the range of the updates as they come in. So that's going to keep on until it gets closed. And then as each one comes in, we look at what kind of thing it was that's been sent to us. Have they sent us a command? Have they sent us their location? Or we're going to assume if it's neither of those things, it's just some text. And then in each of these, we've just got a bit of dummy code which just says, oh, well, it was an update, it was a location, and whatever. So let's run that and see what it actually looks like. So we say go run, and that's going to spin up the bot. It's going to say, okay, now we're running and we're listening, and I can click on this here, and this is going to go and launch the Telegram bot. And we can bring that onto the screen here. We can do this, so you just see the actual thing itself, and it looks like that. So here's the Telegram bot. You can see I've been playing around with this already. But if I move this so you can see both the bot itself and the code in the background, if I say hello, we can see over here, it says hello right back at you. We can see in the bot itself, it logged the fact that it received it. And we can see that, and we can see it logs it down here. We can send my location to it. So we're building up the pieces here that are going to be useful for building a bot that's going to interact with us at the car parks. So if we just click on somewhere on the map and send that as a location, you can see we received the location over here, and you get the longitude and the latitude. So you can do a bunch of cool stuff. And all I'm doing here is sending stuff through this, and it gets sent over there, and we send something back based on that. So that's the Telegram bot, the kind of like the shell of it, and then we're going to build in a bunch more stuff. So to start with, let's think how we're going to get the data in from this REST endpoint that we've got that holds information about the car parks and how many spaces they've got available. So that's actually available. It's a REST call that you can make, and you basically just get a lump of CSV code back. So let me show you what that looks like. So if we run this bit here, And we're going to clear the screen there and paste that in. I'm just going to use curl to go and fetch it. So it's from this particular thing here. So it's the Northern Data Hub in the UK who make this available. And you just get a lump of CSV back. You get the header, and then you've got the different fields. So there's several different car parks, and you've got stuff like the capacity, you've got the available spaces, and the location of the car park. So what I'm going to do is I'm going to stream that information into Kafka, because Kafka is going to be our persistent data store here. We're going to use it for being able to sort through these events, being able to materialize state over these events, and do a bunch of useful things with it. So to do that, to get that into Kafka, I'm actually just going to use a little trick here to take the data that comes out of curl, that's called out to that REST API, and we're going to pipe it into a Kafka topic. And that looks like this. So we're going to stick a while loop around it because we're going to keep on polling that endpoint. We're going to do this every 3 minutes. So this is fairly rudimentary approach here. It's kind of not particularly bulletproof, but it certainly works for the purposes of this. And we're going to take that curl, we're going to pipe it through tail to strip out the header. And then we're going to pipe it into Kafka-Cat, which acts as a producer in this case, taking the standard in that comes through the pipes and pipe it into a Kafka topic called car parks. So we do that, and that's going to sit there. Okay, so it's got a while loop on it, so it's just going to keep on doing that every 3 minutes. And if I split the screen here, and if I run Kafka-Cat like this, and we run it with -c instead, now we can consume from that topic, and we can see we've got data sat in that topic. And if I go back up to here at the top, and if I run that command again, and take that -t off so it doesn't echo it to the screen, put some more data into the topic, and we can see at the bottom of the screen there, we've got more data arriving in the topic. So I'm going to leave that running. So at the top of the screen here, we've got our while loop, which is polling the REST API, pushing the data into Kafka. At the bottom here, we're simply consuming from that topic and echoing out to the screen anytime we get new messages. We've got a bunch of CSV data, and we want to do something with that. We want to say, we'll take out the field that holds information about the spaces and the name of the car park, and we want to pull out those things. Because we want to do things like tell the user when there's a car park that has spaces available. Or we want to be able to ask the question when the user says to us, how many spaces does such and such car park have available? We want to actually materialize that state off that stream of events and say, well, currently this car park has got this many spaces available. We even want to be able to do something cool, which is to say, the user says they are here. Let's look at all the different car parks, work out which one is closest, and then tell them which one's closest that has available spaces. So to do that, we need a bit more than just some CSV data. So to do that, we're now going to use KSQLDB. So KSQLDB, it's this event streaming database. It's built on top of Apache Kafka. And if you can distill it down several layers of abstraction, it's just a producer and consumer on data in Kafka. But it actually gives us this nice high-level abstraction on top of streams of data, both to work with them as streams of data, but also very cool to work with them as state. So to take a stream of data or to take a table of a stream of data. So this gets a little bit funky, but we're going to see how it pans out as we go through. So the first thing we're going to do is we're going to create a stream in KSQLDB. And this is kind of declaring a stream on top of an existing topic. We're going to see later on how we can create new topics that are populated through KSQLDB. For now, we're simply saying we've got an existing topic called car parks, and the data is delimited, it's comma delimited, and here is the schema of that data. So the schema we've taken from the headers that came through in that CSV file, and then the data types we've had to figure out, and it's like, well, the capacity is an integer, and the latitude, longitude are double, so we've had to do that bit ourselves. So we create the stream, and with a stream created, we can actually now project some particular fields from that payload. So we can do this. Go back to the beginning of the topic, this auto offset reset, and now just give me some of those particular fields from this stream. Saying emit changes, should show me the data as it changes, just show me the first 5. So saying, okay, here you go. At this particular timestamp, this particular car park had this many empty spaces. I could leave it running, so let me take off the limit, and it says emit changes, and that's just going to sit there, and it's going to keep on ticking over until we get new data arriving in the topic, and then it'll update it on the screen. So that's our stream of data, and with that stream of data, we can now process it further. We're going to do a few things before we actually start building it into the Telegram bot. We're going to take this date and time and we're going to build it into a proper timestamp because we're going to do some kind of time calculations on it. We're also going to take that latitude and longitude that we've got and we're going to build it into a struct object. And we're also going to reserialize the data into protobuf because the schema is really important, and having to declare out that specific schema every time we want to use it, it's inconvenient for us. It's also really inefficient and error prone for all the other people who probably want to use that data as well. So we're going to declare a schema up front, we're going to store that schema in the schema registry, we're going to serialize the data using protobuf, and now anyone wanting to use the data, us, anyone else who has access to it, can just pull down the data and have the schema already. So let's see how we do that. So again, we're going to say set the offset to the earliest to make sure that we're processing all of the data in the topic. And now we're going to do another create stream command, but this one is going to say I would like to create a new Kafka topic and I would like to populate it with the results of a select statement. So it looks fairly similar, create stream car park, but now we're saying we're going to change the serialization that's being used. So we're going to serialize it into protobuf, and we're saying as the results of this select statement. So I could run that select statement on its own and it would just echo it out to the screen, but this time we're saying we'll take that and instead of echoing it to the screen, write it to a new Kafka topic. And it's a continuous query, it's going to keep on running. So as every new message arrives on that source topic, it's going to get processed by this select statement, which runs continually. We're going to take the timestamp, we're going to create it into a proper timestamp format. We're going to take the latitude, longitude and build it into a struct. We're going to serialize all of that into protobuf and write it into a new Kafka topic. So we set that running and it'll say, okay, I've created a new stream, I've set the query running. And we can say, show streams. It says, okay, you've got a new stream. Here's one called car park events and it's in protobuf. And we've got a new Kafka topic of the same name. So at this point, anyone can connect to our Kafka cluster and they'll see a Kafka topic called car park events, and they could read from that topic, deserialize the protobuf and use that data. So you can actually use KSQLDB simply as like a stream processor that takes some data, does some stuff to it, writes it back to a Kafka topic, and now other applications can use that data. So we're going to do a little bit more than that. What we're going to do is we're going to say, well, let's take that data. Let me just show you what it looks like, just to show that it's definitely working. We're going to say select the timestamp, and now we're going to take the timestamp that we created and actually format it back to our own timestamp format that we can see that's human readable, because it stores timestamps as big int epochs, and then the name of the car park and empty places from here where the car park matches a certain name. This is okay, we've got 3 different readings for the Westgate car park. We got 2 at this particular point, which is at the beginning there when I was kept on running that curl command, and then we've had another reading here. Here's the number of empty places, so we can see 2 more people arrived at the car park, so the number of empty places has gone down, but we've got that data as part of a stream. So what we're going to do now is we're going to create a materialized view on top of that stream of events. This stream here already gives us the ability to answer the question, tell me when a certain car park has got more than a certain number of spaces available, because we can run a select statement. In fact, let's do this. So run from here, and instead of where name is Westgate, we're going to say where empty places is greater than, let's say 100, and emit changes. Oops, get your keyboard right. There we go. So now we've got a query that's just going to tell us every time we get a new message that arrives that matches the predicate that we specified. So the predicate up here where empty places is more than 100, we're going to get a message pushed to the screen. And what we can do is we can run that from a client and say, well, the client's going to receive a message every time a message meets that criteria. So we'd probably run it with the offset set to latest. So let me show you that. So we've got latest here. And now when I run that, it's just going to sit there. It's going to say, well, I'll go to the end of the topic. And now any message that arrives subsequently meeting that criteria will get echoed out to the screen. So that's how we can satisfy that first requirement of tell me when a car park becomes available with a certain number of spaces over the threshold. So this is called a push query. So that's the first one. The second one we're going to do is we're going to say, I would like to know how many spaces are available at a specific car park now. I would like to do a key value lookup. I would like to take this stream of events and I would like to do a lookup against that. And with KSQLDB, and this is where the DB bit of the name comes in, you can actually materialize that state within it itself. We don't have to take a stream of events and shove it down to another data store somewhere else. We can take a stream of events and materialize it within KSQLDB and then do lookups against that state directly. So let's see that. And to do this, we're going to create ourselves a new object. But instead of creating a stream this time, we're going to create a table. So a table is key value state. And the state is going to be things like the number of empty places or the percentage full. And the key is going to be the name of the car park. So the name of the car park is our key. The value is all the other pieces, so like its location and its percentage full. And you can see we're using key SQLDB and we're running a bunch of SQL. We're doing functions and calculations, and we're changing schema because we can use the as operator to change the name of a field. So we set that running and we go and create a table. So now we can do this kind of key value lookup. We can say, I would like to know how many spaces are available at a particular car park. And you'll notice here I don't say emit changes. Here I'm just saying I would like a key value lookup. I would like to pretend that this is a database, which it kind of is if you squint. I would like to say, what's the current state? And it says, well, here is the current state, and then query terminated. So the latest timestamp was this. This is how many spaces there are currently. Has that changed? I don't know. I'll have to rerun that query. As opposed to a push query, where we say, here is the current value, or here is the current value when we get one in, and any time it changes, the emit changes bit, we will tell you it has changed. So pull queries, key value lookup point in time, and push queries, as and when it changes, tell me about it. And we can say, do that from the beginning of the topic or from the end of the topic. So this gives us our tools with which we can now pull into a Telegram bot all of these different bits of data that we want. So let's go and have a look at what that looks like. And let's set it running, and then we can have a look at the code as well. So go run. So this is going to spin up the Telegram bot, and it's going to say, right, I'm now listening on this particular place here. So I've launched my Telegram bot, and I'm going to click on start, which will initiate it. And you'll see by clicking on start, that actually sent a command through, which got logged by the bot on the code here. And we can see here, we get a little prompt telling us what we can do. So this is where we can use alert to receive alert when a certain number of places are available. We can give it a name of a car park, and it's going to tell us how many spaces. Or we can even send it our location, and it'll tell us which car park is closest to us that's got more than 10 spaces available to it. So let's set an alert to start with. I would like to know when a car park becomes available, or a car park on the REST API says I have more than a certain number of spaces available. So tell me when a car park has got more than 100 spaces, or let's say 500 spaces available. So we've set that up and it's created that alert. You'll see here in the code, it's on the log file, it says, okay, we've received that alert. In the background, that's now set running a query saying select from the car park events, blah, 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 where empty spaces is greater than 500, because 500 was the value that we gave it. So now anytime a new message is received on that topic, like now, it will do a push alert out to the user saying, okay, we've received an update and these particular car parks have got more than that number of spaces available. Let's try another one. Let's say, okay, there's a car park called Westgate. I would like to know how many spaces it's got available. So we send it that, and now it's doing a key value lookup. It's doing a pull query against KSQLDB. It says, okay, it's got this many spaces. Also, it'd be kind of interesting to know, well, nearest to where I am, how many spaces available are there? So let's zoom in on the map and give it a particular location, and we'll pretend we're about here in Bradford or in Holmfirth, and we send it that. It says, okay, I'm going to go and do a lookup against KSQLDB, and I'm going to find out which car park is closest. You've got all the kind of some debug information here, and it says, okay, the nearest one is this particular car park. So you can see actually in the debug information in the background here, we can see this many spaces are free, and it's done this calculation, which one is closest to the user. So it's just got a geodistance function as part of it. So that's putting it all together. We've got the Go code is doing the lookups out to KSQLDB. So we can go and have a quick look at that. The first part of it simply takes the updates as they come through. And we've got this one here, says if it was a command, look at what kind of command it was. If it was an alert one, then we're going to pull the threshold out of the arguments. So we say /alert 500, takes that 500, and it passes through as an argument. So we've got a function here called alert spaces. And what that's going to do, if we go to the definition for that, we can see over here, it's now going to go and run this command against KSQLDB, saying select from car park events where empty places is greater than that threshold, emit changes. So that comes through, we do the request against KSQLDB, and we wait for the data to come back. As it comes back, we put it into these Go variables, and we return that back out to a channel. That channel comes back and it sends it out to the user. As we can see here, it's just popped up in the top right hand side. The next part of it says if we get a location come through, then we take that location and we run this get closest, which takes the latitude, longitude. It does a lookup against KSQLDB. This actually does a select against that event stream from the beginning. And then it says, well, take the latest one and just cut it off. It's not actually key value lookup as such. And then the last one itself is doing a check spaces. So it says, well, we've sent the name. We said like Westgate car park. How many spaces does this one have available? And this one, we do a pull query against KSQLDB. So you say, go to the definition. And here it's saying select the number of empty places from the car park where it matches this name. It does a REST call against KSQLDB. And it passes the message that comes back into these particular values and passes it back as a return from that function, which then sends it back out using the bot API. So that's the Telegram bot using Go client to be able to pull messages from KSQLDB using both push and pull queries to subscribe to changes or do key value lookups. The last bit I want to show you is another validation of why we want to use Kafka as the platform for this, because you can use the same messages that we're using to build out state and do push notifications to also stream the data that we've enriched and processed and push that out somewhere else for analytics. So from KSQLDB, you can interact with something called Kafka Connect, which is a great way for integrating different systems with Kafka, both inbound and outbound. So now we're going to push data from that topic of car park information, and we're going to push it down to Elasticsearch. So to do that, we're going to say create a sync connector, take data from this particular topic here. It's in Protobuf because we serialized it as that, and go and push it over to this Elasticsearch endpoint here. So we go and create that. We say show connectors and make sure it's working. And it says, yep, we're running. And now we can go over to Kibana. And in Kibana, we can now analyze the data that we've got within Elasticsearch. So we'll create ourselves a index pattern like this. And the timestamp field we're going to use is TS. And if we have a quick look at the types of data that we've got within this, you can see we've got the capacity, we've got the name, and we've got longitude, latitude. And if we change this like this, we can see down here we've got a location field, which is a geopoint, which is one of the reasons I took that longitude and latitude and made it into a struct, because it means when you push it to Elasticsearch, it kind of just works. So we've got the geopoint, which means we can do some cool stuff with it. We've also got the empty places as a number, and then we've got the name of the car park here, so we can do some analysis on it now. So let's do that. Let's head over to here, and we've got the visualize option and create a visualization. We're going to use Lens, which is kind of cool because we can say let's take the empty places, and I'd like to break it down by timestamp going across here, and I'd like to use the name and break it down by that. So you can say show me all of the different car parks, or show me 10 of the car parks, and instead of the last 15 minutes, show it for the last hour. And you can see obviously in the last half an hour or so, there's not been a great variation in the number of places available, but you can see you can start to plot this information out, and it makes it nice and easily accessible. You can collect the data over a great amount of time and see how it varies and do lots of nice things like that. So we can easily plot it in Kibana. We could use that as a dashboard, a real-time dashboard on top of the data from an external REST API, or indeed from anywhere else, because you can integrate numerous different systems and databases and message queues with Kafka and then push that data straight down to somewhere like Elasticsearch to use it for analysis. We can also say, well, let's take that data, and because it's got a geolocation within it, we can actually start to plot that on a map. So you can say, well, here's the maps part of Elastic, of Kibana. I'm going to add a layer over here and do it as a heat map based on the car park events. And we've got the location field is our geospatial bit. And then the metric we're going to use, let's do it based on the empty places. And we can do that and that and save and close it. And now if we fit it to data, we're going to zoom all the way in, and we can see here's Bradford in the north of England where the car parks actually are. And as that finally catches up, it can see, well, it plots where those car parks are, and it's doing a sum of the empty spaces. So it's not saying in this particular location there are this many, but within this timestamp here, so within the last 15 minutes, there are this many different spaces available. So you can see, okay, I'm going to go to this part of the city or this part of the city and zoom in on it like that. So there are different ways you can use the same data. All of this coming from CSV data on a REST endpoint, streaming it into Kafka, using KSQLDB to enrich it, to process it, to reserialize it, doing materialized views on that data, doing state value, key value lookups, using an external client, REST API. We can do event-driven notifications, again using that external client, use Telegram as the platform for that. We can also push the same data down into Elasticsearch and build an analysis on top of it like that. Okay, so hopefully you found that interesting. There's a few little links that I'd like to share with you. If you want to go and try all of this out, you can do so on Confluent Cloud. Confluent Cloud gives you Apache Kafka, it gives you KSQLDB, it gives you Kafka Connect. There's a bunch of different money off you can get from your bill when you go and sign up. There's a discount code there you can use also. So this lets you just spin up Apache Kafka and go and try it out. Makes it nice and easy to start with. When you want to learn more about Kafka, so you've got Confluent Cloud, but what do I do with it now? You head over to developer.confluent.io. There's a bunch of tutorials and podcasts and videos to help you on your learning journey with Kafka, with Confluent Platform. And finally, come along to the Confluent Community Slack group. You can join the different channels there and hang out with the community, help other people, get help from other people in all sorts of aspects around Kafka and Confluent Platform. So hopefully that's been interesting to you. My name's Robin Moffat. You can find me on Twitter @rmoff. Send me a tweet if you liked it, send me a tweet if you didn't, but be constructive, be friendly. It's always nice to hear from people. So with that, thank you very much for your time and have a good day.
Thanks, Robin. What an incredible talk and demo. Addressing the true pain points in our lives. If only we had IoT devices for every parking spot which we could feed through this pipeline. We'd never need to go searching for a parking spot again.
I absolutely agree with Leo. Thanks, Robin. Let's move to some question and answers. So we have one question here. How does KSQLDB scale for larger production workloads?
That's a great question. So KSQLDB, just like Kafka Connect and all the other components of the Kafka ecosystem, is a distributed system. So you can deploy a single node of KSQLDB, or you can scale it out and it will process the data in parallel. Unlike like a typical database, you don't just deploy one KSQLDB cluster. You would think more of deploying KSQLDB applications. So in the case of the demo that we saw with the car parks, you might have a KSQLDB application cluster that will be supporting that particular purpose. And then there might be another one somewhere else supporting like payroll or inventory or whatever other applications and services that you've built. So you scale it out within the context of that particular application or purpose which you built it, and you add in nodes and scale it out horizontally like the other pieces of the Kafka ecosystem.
Awesome. I have another question. So I'm thinking with SQL, you end up with these large, complex joins. How would KSQLDB manage with large, complex joins?
So that's something that's evolving all the time with KSQLDB. Initially, you could only do a join between two different objects. So a stream and a stream, or a stream and a table, or a table and a table. I think just recently we've added multi-way joins, but typically the approach you would take would be to daisy chain the joins together if you have to, if you can't do it all within one query. In terms of the scale of it, if you're processing the events as they occur, it's less about taking like a huge big block of data and kind of like crunching that down as we would do in like typical data warehousing. And it's more about like as each event comes through, maybe joining it to the particular dimensions or whatever to denormalize it down. But the joins is something that's being kind of evolved continually.
Yeah, awesome. Good to hear some of the tips and tricks. I have another question. So what are some kind of advantages over KSQL as to other tools? So I'm thinking stuff like Kafka Stream, Spark, or Flink.
So I think a similar question came up in the previous talk and Marta answered it really well. A lot of it comes down to your use case and your existing technology stack. Another thing is how you actually want to be processing your data. So if you want to process in batches or micro batches, then you wouldn't be using something like KSQLDB or Kafka Streams for that, because this is proper event stream processing. So as each event comes in, we're processing it. In terms of the difference between Kafka Streams and KSQLDB, KSQLDB is actually built on top of Kafka Streams. So there, if you're a Java coder and you would rather use a Java library for your stream processing, you'd use Kafka Streams. It's part of Apache Kafka, and it lets you do all your stream processing there. And so everything that you can do in KSQLDB, you can do in Kafka Streams. If you're not a Java coder, or if actually you prefer the simplicity of just typing a line of SQL instead of writing a whole bunch of boilerplate and so on for your Java code, then you can use KSQLDB. So it's kind of the appropriate tool for what you're trying to do.
Thanks, Robin. To our audiences, Robin will be available on Slack to answer your questions further. We'll have QR code coming up now. If you would like to rate Robin's talk, please scan it. Thank you.
Capture the mic.
Oh, yes. So what an awesome conference and what an awesome day of data engineering it's been, Simon. What do you think?
Yeah, I've enjoyed everything today. We've had some amazing presentations. We've had some incredible questions and some really spot on answers from our audience. And it's had a really incredible vibe. I've loved the diversity of speakers and the incredible content that we've had today.
Yeah, it's been wow, is that a cat, Simon? Did you?
It absolutely is a cat. And I think Snowy the cat actually is here just to remind me that an event like this is only possible due to the amazing support of our incredible sponsors. So I'd just like to take a moment to call out the support that we've received from Cloud Shuttle, Yao, Canva, Instacluster, ThoughtWorks, Microsoft, Confluent, Fivetran, AWS, Databricks, MongoDB, and Snowflake. Without their support, an amazing event like this just would not be possible. And over above that, I really wanted to call out the support of the amazing community who's come together and helped put on this amazing event today.
Well, thanks again, Simon. We're going to put up the day 2 agenda now, and we'll see you bright and early. We're kicking off at 9 a.m. GMT plus 10 or Australian Eastern Standard Time. So see you bright and early in the morning. Ciao for now.